will delay and it is unnecessary making fuss because this is webcasting also there, and this is a Ministry of Education's very premium kind of course for the international collaboration, and rare to rare people only get this grant to organize the GIAN program. And it is fortunate that our department is organizing this program second time. And I am lucky that I got 2 times. This is the second time. And actually first time itself I have submitted two proposals. One is Professor Dorel's along with Professor Dorel Mihach, and another with Professor Brinde. So after that the COVID has come, and then I don't know, there is a shifting of the national coordinator from IIT Kharagpur to IIT Hyderabad, and because of that the delay was done. Finally in 2023, sometimes in March or April, they asked me to resubmit the consent from taking Professor Brende. So we have requested, and he sent the consent. After that we submitted, and around August first week we got the confirmation that your program accepted. Send the brochure for the program, as we can send the grants for the same. So they have sent the acceptance and all such things. Those who are the faculty members of Indian universities, they can also submit GIAN phase 5. It is now closed, is going to open in January 2025, 1st January 2025. And most probably I am in a mood to submit another proposal jointly with some computer people and one with some other mathematics people. If possible, I will take some of my colleagues as well as some of my students also. One in data science and another in functional analysis, but on the applicational part, so that we can shine more. So let me introduce our welcome our Professor Bhinde. Welcome, sir, for this session.
Thank you.
Yeah. So he will speak on introduction to metrical fixed point theory and applications, what he talked yesterday. So he will continue the second part today. So Professor Biren.
Hello, good morning. Nice to see you again this day, very sunny day. In my country, I am very excited about the weather because in my country it's -7, -8 and snow, so here is really beautiful, so we don't need hard clothes. I want to take first the opportunity of this announcement by Professor Murthy, and would like to draw your attention to a forthcoming conference. Maybe some of you can still register, I don't know. KFU PMs, just a moment. There will be a conference 1 month by now in the King Fahd University of Petroleum and Minerals. And it's related to what Professor Murthy was saying. The conference is very interesting. Even the title is very suggestive, Maths Connect. And it is about mathematics and connections to to other fields of research. And to this conference, I'll give a talk about fixed point theory and connections to combinatorial optimization. Graph theory in general to celestial mechanics and unfortunately I did not consider data science, but it's in astronomy. So some of you could, I'm sure, I don't know if the website of this conference is ready, but I'm sure there will be some speakers who will be involved in data science.
Yes.
For sure. So just look for this. Maths Connect is 10 to 12 December 2004. I haven't time to look on this website if it is ready or not. So it could be very, very interesting and informative for most of you. Coming back to the topic for today, so in connection with these applications, a lot of our colleagues are making some critics to specialists working in fixed point theory, at least in my country where we have a very strong group of research, that we do not consider a significant number of applications. So this is the main point. So you are too theoretical, too much theory, and you should consider applications. And in this respect, I would like to tell you that this is a very old polemics. I have shown you yesterday the polemic started by Fourier. Fourier is famous by Fourier series, and he was very applicative mathematician because Fourier series were introduced because of applications. And he said number theory is not important, so it's just a game, so nothing important. But these polemics about pure mathematics versus applied mathematics is very old. This is a problem that was stated and discussed in Soviet Union. During the 50s, 60s, Russia, it's a big force in mathematics. Till now, they produced very important mathematicians. And in Soviet Union, in Russia, it was this discussion. Applied mathematics is not very deep mathematics. And we are doing pure mathematics are important, and the other said, no, pure mathematics are not useful, so do not consider pure mathematics, only applied mathematics. And this discussion was very deep related to the research at that time. In the 50s or 60s, if you know, there was the first flight to the moon, the first rockets, and then all this research was devoted to such kind of activity. So applied mathematics was very, very important. But one academician, a Russian academician, in such a polemic, he said, okay, look, stop to do pure mathematics, and you will reach one day when you will not have what to apply if you do not produce pure mathematics. So we have to produce pure mathematics, but sometimes to show that this pure mathematics is connected is strictly connected to some fields of applications, and if possible, we should give some applications. Now, I will speak you as an author, as a researcher, but also as an editor and as a reviewer. Now, this trend is that in a paper on fixed point theory, it should be included an application. So this is the main objection of reviewers, of editors, include an application. Okay, you have a paper of 8-10 pages, theory, and if you include a serious application, you need other more 10 or 12 or 20 pages. So most of the authors are including trivial applications. So most of them are trivial. What does it mean trivial? Just so this can be applied. And sometimes it's the same kind of problem, change it a little bit. And I would like in this context to not speak about applications of fixed points to usual problems like differential equations, all kinds of differential equations. Now, is this new field fractional differential equations and all kinds of integral equations. The approach for all these problems is very simple. As I said, we transform equivalently the original problem into an operator equation, and then we apply a fixed point, an appropriate fixed point theorem to this operator, and we establish existence and uniqueness if possible, and if possible, we indicate a method for approximating the solution, the fixed point. This is the typical applications. I would like to speak today on another kind of applications. If you are not familiar with this kind of applications, just search in any database like MathSciNet for differential equation and fixed point, and you'll find a lot of papers, and you can see how a differential equation is transformed by a green function in an integral operator equation, and the others similarly. For integral we have Volterra, Fredholm type integral equation, or combination of them. So today I want to show you some application. It's a very particular application to functional equations. What is a functional equation? Okay, differential equation, fractional, differential equation, integral are all functional equations. But by functional equation, we basically understand an equation which involves a function as an unknown, and we intend to find this function. Of course, differential equations are functional equations that involve the derivatives of the unknown functions. Fractional differential equations, similarly, integral equations, they involve also the integral of the unknown function. But here we have just simply G is the unknown function or mapping here, because we work in a metric space X, D, Y is a Banach space, and the equation is very simple. Just find if F is given, F small is given, F capital F is given, so just find this function G such that this equation is satisfied. This equation has been studied for a long time. I have here some information. So starting with 1960, you can see this is not from Serbia, but from Bosnia-Herzegovina, former Yugoslav Republic. And, okay, even earlier, Germanescu, he's a Romanian mathematician, and he published he studied this, sorry. How can I show on the screen without moving? And also this Polish mathematician Kuczma studied the equation Malenica and in two papers. So very important kind of functional equation. And I was looking to this problem many years ago, maybe more than 35 years ago, when I was studying fixing points for my PhD thesis. I did my PhD thesis late because I worked in computer science for a while, and then I decided I want to do research in mathematics, and I switched from computer science to mathematics. And believe me, this was a very good decision because the temptation was to move in academia for computer science. And now, if I look back, I consider it was a good decision to switch to mathematics. Why? Because I used tools from computer science in my research in mathematics. So I took this advantage in many instances, having an algorithmic way of thinking to work in mathematics. Of course, I have this nostalgia for computer science because I worked 11 years in computer science. I did programming. At that time, programming was totally different of what is now. Maybe you didn't study at the university the history of computer science, history of informatics. A computer was, roughly speaking, this room was a computer. And it has been big pieces of all kinds of electronics, and the total memory of such a computer was 256K. This was the memory, then the whole memory. Now a phone has, I don't know how many giga. Yes, and at that time, the most important challenge was to work inside this small memory and to run big programs. So this was the challenge, very nice challenge. How to use the memory, the memory to work and such. And then, after a few years, this memory increased, doubled actually to 512K. So this was a big progress, and then came this period. Now it's really incredible for people who worked at that time in computer science. And let's come back. So I was looking at this paper by Malenica. I have shown before this one. And I realized that what he is doing, he was using something which is connected to fixed point theory, but he was not aware of this. So in solving this equation, a functional equation, he considered such a function because he was working on the real line. He was considering such a function which was supposed to be continuously and strictly increasing, and with these two conditions, the three conditions, and then he used to prove that the sequence of iterates, so this is the Picard iteration, converges to B when n goes to infinity. So I observed that this property 2 is nothing else but is characteristic to what I presented you yesterday, Picard operators, which were introduced by Professor Roos. And you remember what is a Picard iteration? I'll show you here the definition for this case. So we have this function here somewhere, B, not A. So this was the idea. So I noted this is a Picard operator, and I solved this equation in the case that we don't work on the real line, but in a general case of a metric space X and Y, the space where we work for this iteration is a Banach space, and I published this paper, an old paper of mine, on the solution of a functional equation using Picard mappings, which was published in this prestigious journal in 1990. This was one paper on functional, maybe my first paper on functional equations at this level. Maybe I should tell you that in Romania we have, in this journal I mentioned yesterday, beautiful journal. This created thousands of high-class mathematicians in Romania. Thousands. Any generation produces this, because this journal contains elementary functional equation. I show just one. Find a function f, this is elementary, such that f of x, let's say x plus 1. This is for secondary school. It's a nice problem, so it's not easy to solve. I challenge you to solve it, and we can discuss in the break. So backing to our functional equation, our high level functional equation. So this is for students of 13, 14 years old in secondary school in Romania. And I have this example. We take, instead of a, b, this interval, we have this function defined in this way. It is discontinuous, so it doesn't fulfill the previous assumptions. And I go to show you this. So it is not continuous. It is f of 0 is not 0, f of 1 is not 1, so neither A neither B is fulfilled, and moreover it is not strictly increasing because it's decreasing. So, however, we have that it has a unique fixed point 2/5. It is a Picard operator. This means this conclusion holds without any of the previous assumptions. So the idea is that the assumptions here were too strong. So what I tried to tell you yesterday is that we have a look on a paper, on some arguments. So at that moment, I contemplated this definition, this example, because this was the main assumption for solving the equation by Malenica, by this mathematician. So I realized weakened these assumptions, and here is another example. Actually, this is an almost contraction, as I presented you yesterday, in the sense, but it's an almost contraction having unique fixed points. The second example, it's an example of a contraction. The same, no one of the assumptions before on F are satisfied, because we have here two fixed points, and it is not continuous, it is increasing, let's say, but is not strictly increasing. And as I presented yesterday, Picard operator means a unique fixed points and the convergence of iterates, and weakly Picard means more than one fixed point, and Picard iteration converges to one fixed point. One more example is this one. I presented yesterday the identity map. It's also such a mapping satisfying the conclusion in the previous example by Malenica, and this is also a weakly Picard operator, and the set of fixed point is the whole interval 0, 1. So here it's an error in my text file. In this paper, we proved that almost contractions are in general not continuous, but if we have almost contraction, then it is continuous at any fixed point. So we can say this way, if we have a point B which is a fixed point of T, then T is continuous at B, but in general T is not continuous. So this is the property of almost contraction. As I insisted yesterday, Banach contractions are continuous. So almost contractions have more than one fixed point, are not continuous in general, and they preserve the other conclusion in Banach's fixed point theorem. Well, to solve this functional equation, I write here, again to have here, to solve our functional equation, we need some prerequisite, because you know what I said about including, so gx, gfx equal capital Fx. This is our functional equation. To solve it, we need some knowledge about series, numerical series and series in a Banach space here, because I could work on the real line, but I prefer to work. Series are studied, I guess, in any university in the first year calculus course. I suppose people are familiar with series. So in the case of a Banach space, we actually mimic the situation on the real line. No, nothing is really different. we have a series of positive terms, let's say, and we have this time n is positive, and we know what does it mean, the convergence of the series. We have criteria to establish if it is convergent or if it is divergent. Here we work in the Banach space Y and consider the partial sums. So Sn is the, you may know it's x1, x2, xn, and the series is convergent. Here it should be xn. Is convergent if Sn is convergent as a sequence. So this is and the limit of Sn, if the limit of Sn is S, then we say that the sum of Xn is S. This is for a convergent series. And we also consider a sum of the partial sums. So we consider this sequence with double indices, Snk, which is defined in this way. Sn of 0 is Sn, and Snk is the sum, the partial sum of order k minus 1. We also consider this sequence Cnk, which is given by Snk over the combinatorial. Here are is the symbol for the binomial coefficient. And in the theory of series, we say that the series S sum of Xn is C0 summable or C0 summable with the sum S if this sequence I put here, C is from C0, converges to S. In particular, if K is 0, we find the usual convergence of series. So this is a concept in summability of series. By the way, I mentioned yesterday an important name in fixed point theory, Billy Rhodes. I mentioned his classification of contractive condition. He was mainly working in this area. He was working in summability of series. And from summability of series, he came across with fixed points. Because I'll speak maybe more, but today I'll speak a little bit about mana iteration. He realized that mana iteration, in how it is defined, is defined through a summation rule. So he came across with fixed point theory, and he moved to fixed point theory for the rest of his career, and he did very nice things. As I mentioned yesterday, he did this nice classification of contraction conditions, and he was before a specialist in summation of series. So we know what is a convergence for series, but we also know what is means for a series to be C0 summable. This means that our series can be convergent, but can be divergent, but C0 summable. So these are the two variants. So we can work even with divergent series, but they are summable in this sense. There was a very extensive literature about the summability of series, And there are many kinds of summability. I just mentioned here this one, Toeplitz summable. This is also related to matrices. And there is also another concept. I'll give you the presentation, the file with my presentations to can read more about this. I do not insist on these facts. So if you are interested, these are about Toeplitz summability. Again, we have a series. Normally it is not convergent, and then we consider an infinite matrix of real numbers. We construct this family of series, and which are assumed to be convergent with this sum, and in that case we say that the series xn, sum of xn, which is not convergent, is Toeplitz summable or T summable with the sum S hat. So this is a second kind of, this is the way Professor Rhodes were led to see that man iterations are related to the summation of series. And there is a third type of summation, is the Abel summation method, and you see the definition. So in that case we have a series. It is summable by Abel's method, or A summable with the sum S. If this series, we insert a t to the power n with t in an interval including -1, 1, if there exists this limit when t tends to 1 increasing. Okay. These are three types of summability, and if someone wants to see more, I was reading before taking the PhD topic in fixed point theory, I was interested in the convergence of series, and I just want to show you, do you know for this series the ratio criterion of convergence? Some of you, did you study this? We have this, if limit of xn plus 1 is k, then if k is less than 1, positive of course, then series is convergent. If k greater than 1, the series diverges, and if k equal 1, we cannot decide. Did you study this? Yes or no? Yes, okay. So I just want to tell you one of my results is not related to, but I used in fixed point theory. I have this limit form can be written under this form. Less than 1, and one of my papers, I was rather young at the time, I improved this criterion in this way, xn here, sorry. I improved this where Vn it's a convergent series. And this is, if a series satisfies this, then it converges, and this is, of course, a weaker form of this condition. So I improved this by putting here term of a convergence series. So just in passing, I wanted to mention it. But we come back to solve this functional equation. So as you can see, I mentioned at the beginning, to consider an application of a fixed point result is not easy. So we have to build the entire prerequisite, what is needed to present this application. You can imagine if you include this in a paper with a fixed point theorem, a lot of material we have to include. So this is why we should be reasonable. So here are some results about the regular metrics, infinite regular metrics. I don't insist, and about the convergence of the series in a Banach space, because I want to move. Here is another theorem about the convergence of series in Banach spaces, and keep in mind that infinite regular matrix is directly related to Mann iteration, to Krasnoselsky Mann iteration. I'll speak on this later. And these are constructed by using a particular infinite regular matrix, any such iterative sequence. So coming back to our functional equation, this one, how we can solve it? It is not easy to anticipate how we can solve it. So we actually start from, I put here a general result. I mentioned yesterday, a enormous contraction is a weakly Picard operator. So the result is given for weakly Picard operators, but in particular it is valid for almost contraction. So we consider F a weakly Picard operator, and the next small x in capital X arbitrary. By the definition of the weakly Picard operator, for any x, we know what does it mean, a weakly Picard operator. For any x, Fn x goes to, I said, a B, which is a fixed point of F in this case. So all the time, this means that it's a weakly Picard operator. So we consider this series. Look at the functional equation. F is in the right-hand side, and F is in the left-hand side here. So by considering this series, we can find sufficient conditions to ensure the existence of the solution for our functional equation by considering the convergence of this series or some summability means. So here it's the main result. I'll try to make it clear. We have, in general, weakly Picard operators. And we work in a complete metric space. Y is an arbitrary real Banach space. F, this one is a given weakly Picard operator, and F, capital F, is a given mapping. No special assumptions are needed for capital F. And we only suppose that capital F is continuous at B for any B, a fixed point of this map F. Then we have these four conclusions. First, in the case our series, our previous series, if it is, we can see how you call, we call alternate series. Do you call alternate? Because the sign changes. We call alternating series. This alternating series, if it is convergent, then its sum, let's say G, it's a solution of this functional equation. Moreover, if this f, small f and capital F are continuous functions, continuous mappings, and the series is uniformly convergent, then the solution is continuous. So it's very important. We have here, in fact, the solution exists, first part, and the solution is continuous, second part. So we can ensure the existence of a solution for this functional equation, and we can ensure a continuous solution. So the others are the three types of summability. So the series, in case our series is not convergent, but it is T-summable with this matrix K, T, which is a regular matrix. I don't insist on this concept. So we have the, I did not include it here, some assumptions on this matrix T. Then the sum of this series, the sum G, is a solution of the functional equation. Of course, it will be not continuous for sure. If we have Cesaro summable series, then again the sum of this series is a solution of the functional equation. And of course, in the case of the Abel summability, we have again the same conclusion. So this is what we can say about this functional equation. Look, the main tool here, the main tool was the fact that our map F was a weakly Picard operator, was almost contraction or on another kind of contractive mappings which ensure that we have weakly Picard operator. In particular, of course, it can be a Picard operator, and this is one application of our result, our results about almost contractions in the class of functional equations. Okay, as I insisted yesterday, I pretend this is a new result, the preview theorem. This is a new result, but I pretend. So to complete my approach, I should prove that this is really effective generalization. So keep in mind, this is important. Believe me, I've seen a lot of papers. This is a generalization of this result. I don't believe this. I don't believe if you do not show concretely that indeed there is a mathematical object that fits this new result and does not fit the other one. So this is the supreme proof that your result is new. Your result is a generalization, is above the existing one. And this is a simple example. I have actually two. So we consider, okay, examples should be simple, believe me. Examples should be as simple as possible, but just to prove our assertions. It happened to me many years ago. I'm remembering always smiling. I was very young. I attended a conference. And at that time, I was working on Newton-type methods. I applied fixed point theorems to prove the convergence of Newton-type methods. And the results were quite nice, quite general. And I had an example. Newton method, as you may remember, ask for continuous second derivative. This is important assumption. But I proved the convergence just assuming the continuity of the first derivative and some other properties of the first derivative. And I gave an example, I do remember, very nice example, of a function which was not twice differentiable, it fulfilled, and the example was nice, and after I presented my talk, one colleague of Professor Rus, my advisor, very kind person otherwise, Professor Mikula, maybe you didn't know. He was alive, I guess. No, he was not. He died rather young. No, Mikula, not Rus, is alive, but his colleague of department. He asked, he said, Vasile, but this is a very simple example. Could you give a more complex? And Professor Rus exploded. Why? We need just a simple example. It's as simple as possible, just to prove our assertion. But he said, okay, I would like an example, this professor, Mikola said, I would like an example in maybe differential equations, something very complicated. And Professor Rus, and I follow him totally in this respect, said no, we need a simple example. So this is a simple example. Look, we have the unit interval with usual norm. We take f small and capital F in this way. So f is x over 2 for x 0, 1, and f1 is 1 over 3. It's not continuous. Fx is also, again, not continuous mapping, not continuous function, and it is easy to see that f is a Picard operator. It has a single fixed point, and we have this. We can compute fn of x, and then fn of 1, and we can see that for x1 is our b in that case, we have this result. So the first condition is satisfied. So this is a Picard operator. So in that case, our b is 0, and we can see that f, our capital F, is continuous at 0. So this assumption in our theorem is also fulfilled. And moreover, this series, in that case, if we compute all, is this series which we can compute always. So our function, the unique discontinuous function is the solution because we have some extra terms here. So our function will be this. G of x is x over 3, and g of 1 is 2 over 9. So it's a discontinuous solution of our functional equation. Why is discontinuous? Because this series is not uniformly convergent. So this is one reason. This is one example, simple example. So what does it mean? It means that this conclusion 1 is, and also f is not continuous. Sorry, so there are two reasons.
It has fixed point 0.
Yes, but the point is that also f is not continuous because in we have these two conditions not satisfied. F should be continuous on the entire entire set, and this is not, so the series is not uniform. So this is why our solution is not continuous. Then another example similar to that, but f is different. So here we have the same. We have convergence, and we can see our series, this series does not converge for x equal 1. So we cannot apply the first conclusion in our theorem but we are able to show that for x equal 1, this series is summable, and its sum is g of 1 over 2. So in this case, g given by 0 for all x in 0, 1, and g of 1 over 2, then g is the unique discontinuous solution of the functional equation 1. This is our functional equation. So, what I suggest here is to consider other type of functional equation. I suggest you, it's an important topic. So this is one type of functional equations. There are many. This one. So there are many. So study, this is my suggestion, study with the same tools other types of functional equations. To my best knowledge, there are not results regarding the solution of such functional equations using fixed point tools of this kind. So I guess this would be a very interesting topic to work on. Also, I would be interested if someone, here the two examples, F is a Picard operator. This means the set of fixed points of F is only one point, so B. My challenge is to find example when F is weakly Picard operator. I have given in the talk yesterday some examples, and I guess it is possible to construct. I did not construct an example for this kind of mappings, but if we go back to our convergence theorem, so we see that normally we can work without any difference. So we have F, which is a weakly Picard operator. This means fix of F has two fixed points or more, and then for each fixed point we have this. Then we can have one conclusion, 1 or item 2 or item 3 or item 4. This is mainly what I wanted to show you about applications to functional equations of the theory of Picard operators and theory of weakly Picard operators. This means applications of fixed point to this kind of functional equation. Look, other types are suggested here. This equation, which is called Steinhaus, after the name of a mathematician, I didn't mention here the paper by Steinhaus. It is old. This should be another kind of equation. If you remember, so our equation was this one. Okay, this was our equation. And look, Gerchevanov studied this equation where AX is it's a function. So this was again on the real line. This is a challenge to do this. And this was, you can see. I am curious. I had no time to look on the, when I try to find what other mathematicians did, usually, and I suggest you to do the same, usually I go to this paper, and in some databases we can find citations, so we can see. For example, papers by Professor Viramani, if you look, hundreds of citations. So in order to know if you can do something there, you should check, because hundreds of mathematicians had work on, for example, on cyclic or on best proximity. So it's not easy, but we look to what other mathematicians did, and we can decide if we have chances to do something new. So this is a new topic. So it can be done with almost the same means. In my opinion, it works without any change, just we need to take care of this A of X, which in our case is the identity, so it's 1. So this is not easy to, then in order to reach an approach to this equation, maybe first we should go to this equation, which was studied by a Romanian mathematician, Germanescu, in �56. And what he did here, you see, we had only, he had constants, A0, A1, A2, AN are constants. I did not mention here. And he used G of Fx, G of F2 are the iterates, and this is more closer to our fixed point approach because the iteration is here. And he obtained very interesting results. So these are two types of functional equations at least, but we can combine also these ones. So this is the application of almost contractions to functional equations and to of weakly Picard operators to functional equations. Of course, that this is not a typical application of fixed point theory, and most of us are now interested to find application in machine learning, data science, what is now of current interest. But always you'll see that such a problem can be related to some current topics of research. It is my belief, I know in my country there are some mathematicians, they say, you are working in this topic. This topic is not of relevant interest. Or another one, this topic, this is an old and not fashionable topic. This is not, I do not agree with such an opinion. I consider any problem, any mathematical problem is of interest, and we can work on it honestly, and we can try to do something new. And on such kind of problems, just be honest with yourself and tell me, if you look at this equation without knowing anything about it, how could you approach it? It's not easy. So we look at it and what to do. How we were suggested this series we had in the proof? How was constructed this series? This is the question, B here, sorry. B and the others. And there is no easy to see how we construct this series, and how we do in this way. A normal approach is to do G of fx. Okay, then we take instead of x, f of x. Then it will be G f of x plus G f2 of x. Right? And we continue, and we'll have G, how is in the, it's Fn. So G of, it should be Fn minus 1 of x plus G of, n minus 2, Gf n minus is 1, 2, and Fn is right. Let's see. No, it's not correct. So here it's x fx x is n minus. So I write one more. N minus 1 G of Fn equal Fn. So this is the approach. Then we sum all. What happened? I multiplied this by minus 1 because I intend to have them cancelled. So the next one by minus 1, and so on. This one will be multiplied by minus 1, maybe to n minus 1, and how is there? Minus n multiplied to minus 1 to n, and we sum, and we should get exactly our series. So the rod from the original functional equation is this one. So we applied actually an iterative approach to reach this series, and this was the secret of the solution of this functional equation. So to anticipate and to find this series, and then to study the convergence of the series. So let us conclude all for this topic. Because I mentioned Maths Connect, what kind of knowledge we collected in this application? So first of all, we had functional equation. Then, in order to tackle this problem, we had fixed point theory. Then we had theory of series. Okay, and and here also summability, which is an advanced field summability of series. And in this way, we were able to solve. So actually, three fields unified to solve a problem. When we consider other kind of applications, if you consider now this machine learning, maybe I'll try to speak about some relation Maths connects to of fixed point theory to data science. I forgot. I promised you, but I forgot. Then we can see how we can relate these two fields apparently totally different. Fixed point theory, data science, fixed point theory, machine learning. Fixed point theory has very important, by the way, in theoretical computer science, It's extremely, extremely important, fixed and point theory. Mainly, I take this time because there are a few minutes until the break. We are all familiar with metric spaces, but there are many generalized metric spaces. One such metric is, how is called, not quasi-metric.
What is the condition?
It's in computer science. I don't remember now the name of this. Partial, thank you. Partial metric.
0 and 1.
Yes, partial metric. It has been introduced in computer science, and I have in work a paper. We work on it by half a year now with Professor Roos to the applications of generalized metrics in theoretical computer science and formal languages. A lot of application. For us who are working in fixed and point theory, partial metric spaces are not relevant, in the sense that any partial metric generates a metric, so for us it is done. So we can convert any result in, but for them it is very important, very important. And also I'll speak to this conference Maths Connect about this very important generalization of metric spaces, B-metric spaces, which is extraordinarily important also in combinatorial optimization, in graph theory, in celestial mechanics, in astronomy, a lot of interesting application. But this structure, this setting, is also very important for fixed and point theory. There are hundreds of papers in the last. I'll tell you just a few words because I'll have no opportunity to speak later on this. I worked on this in 1993. There was another mathematician, Czerwik, a Polish mathematician, the same year. My paper was published in Seminar of Fixed and Point Theory. It was not so visible, but his paper was very visible. It's extremely cited, extremely highly cited. And he has another one, 1998, I suppose. And recently I published a paper about these B-metric spaces, and I discovered that I was at a certain time persuaded that the first paper, the first fixed and point theorem, was in this year, Russian mathematician, Bakhtin. But recently, maybe 2 years ago, I discovered that it is not true. The first fixed and point theorem in such B-metric spaces, exactly the Banach fixed point theorem in B-metric spaces, was established by other Soviet mathematician. By the way, this is a Romanian one, but in Republic of Moldova. Moldova, it's a part of Romania that was taken by Russia 200 years ago. And Russian, what they take, they will never give back. So this is the Russian principle. Yes, yes. And Vulpe means fox in Romanian. So Vulpe is the name of this mathematician. And actually he was the first one. The second one was Bakhtin. He was not aware of this paper. And Czerwik knew just the paper by Bakhtin. I knew just the paper by Bakhtin, and I extended this. And so, to close our session, first morning session, so I would like to say that sometimes a result in fixed point theory, which is not really significant, can have relevance in another field. So, for example, for this simple case, weakly Picard operators is not a big deal, but here are essential. Picard operator here are essential. The same partial metric spaces in our theory are not relevant because we can construct immediately a metric and the result is equivalent in a metric space, but in computer science it is relevant. So do not disregard result. Any kind of result can have some relevance. This is my personal opinion, and I do not agree with people I mentioned before that say, this is not relevant. This is not relevant mathematics. This is old. This is not fashionable. Now it is fashionable to do this. And mathematics, any kind of mathematics is valuable, and just to be sure, it is new. So maybe some questions. We have time. Yes, we have time for some question, if any. Please feel free to ask.
Yeah, very, I think, informative talk by Professor Brende. If you have any, like, I think he elaborated a lot of things here, especially the starting from the functional equation. The fixed point actually originated from the functional equation, and he was touching the Mann iteration, that you have seen that. Later on, some applications, this iteration kind of things using this operator, and some of the hidden, actually I can say, the researcher whose name not so visible because of the low circulation of the journals, but their works are very nice. Like I think this Professor Kannan also, R. Kannan, his result was published in Bulletin of Calcutta Mathematical Society for the discontinuous functions, and not that much visible, but once he left to US, then you see the difference. And you will be wondered to know that actually he joined in physics.
In physics? Not in physics?
No, first he joined MSc Physics. After that he left physics after some time and joined MSc Mathematics in Calcutta University. I think Professor B.K. Lahiri is his supervisor. Yeah, Professor Kannan's. So that's why I knew. And since my thesis went to Professor B.K. Lahiri, that's the reason that I am very much connected to Professor B.K. Lahiri. And his very small, some 125 pages, functional analysis. And in that you can find very good examples. Like he says, examples means they should be very easy to understand first. So that is true. So any question from the audience in this regard? Yeah, please.
Sir, when you were explaining the result by Roos, your supervisor, there was a result and A and B, two parts. So in part B, it was A and B both must be fixed points. So it is necessary that A is also required?
You mean this initial example?
Yes.
This one?
Yes, this one.
Is not essential here. Here, the authors I mentioned, they wanted to avoid this fixed point because they wanted only one fixed point. They were not able to treat. So what they said, they consider only this. You see, here it's not excluded. I is excluded to not be a fixed point. It's not essential. But in my considerations, this example is all right. So A can be a fixed point. This is the question.
Yes, and also this the third condition, if x is strictly greater than x. So
Oh, of course, is not essential. So I said this is not, any one of these are not necessary. These were given just for the sake of solving this problem. So this mathematician, Malenica, this is a Serbian mathematician, he needed this function f, and he forced to have this structure. So he assumed in his main theorem, these are the assumptions on f. But as I said, these assumptions all are not necessary, are just sufficient for this conclusion. So this was needed actually for him. He needed this, and this was why he excluded a, because if x is a, then what happened? Limit of n of a is a. So he wanted to exclude this. So this was not the general case. So this offered me the opportunity to extend. This was the, as I said yesterday, we have to go deeply into such an example, into a theorem, and to see what is sufficient only and what can be, what is necessary. So here, the only necessary assumption, which is actually a conclusion, is this one. This was the only necessary fact. The other were all sufficient to ensure this. And the point was how to ensure this in a general context. And in the general context was to consider a Picard operator or a weakly Picard operator. This means a fixed point theorem. So behind these are fixed point theorems, but I did not mention. So because we discussed yesterday. So normally we should say that for the mapping I considered here, we have this fixed point theorem. Where is? So for this case, I will say that we have f, which is satisfying a certain condition and has fixed points and so on. So, all right? The answer? Okay.
yes.
Did someone solve this elementary functional equation? This one for students in secondary school. Do we have still 1 minute?
Yeah. We have.
Okay, we have 3 minutes. So
Yeah.
I came back to this equation. Did someone? Something? You had no time to think about. It is very easy. We just change x to be 1 minus x. And this will be our f1 minus x. And this we should x. 1 minus x. X minus x plus 2. And we can see, we can solve this system. It's a system. And we can find directly fx if we solve with respect to this unknown. This is a very nice elementary problem. Okay.
So if no question. So this session is really a very innovative session. A lot of information we have received, especially that area, particularly Romanian. So you can understand that Romanian mathematics is also very sound mathematics, and especially they have worked in functional analysis, particularly deep mathematics is there. Okay, so I should say thanks to Professor Brende for this session. Thanks.
So this will be the second one. Okay. Thank you.
So now 15 minutes for the tea time. again welcome you all for the lecture 2 of the first half. In the first session of the today's schedule, that is introduction to metrical fixed point theory and applications, part B, particularly the applications part. I think most probably it is covered because well in time by Professor Basile Birindo. And now the next talk by the same, because as I said yesterday also, he has some obligations in Romania, and some other countries, accreditation part. So for some time he is not available in the afternoon. So the next talk is under the title Iterative method for fixed points of non-expansive maps. Okay, you have the contraction map and you have the ellipsis map. Now this contractive map also by Edelstein. Now this is in between non-expansive map and treatment of the non-expansive map. Normally if you talk about the norm linear space and T is a mapping from X to itself, then norm of Tx minus Ty is less than or equals to norm of X minus Y for all Xy belongs to X in case of the norm linear space, non-expansive maps. Okay. So for such maps you cannot take the sequence of Picard's iteration and you can't move so smoothly like you are moving with the Banach fixed points. So there are some abstractions, there are some issues why the sequence can't converge, and what is the beauty in considering the non-expansive type maps, non-expansive condition also. Okay, so professor will deal with all such conditions and discuss about this. If time permit, we shall talk something else also. Thank you. Please.
All right. So roughly speaking, the first 3 lectures were devoted to contractive type mappings. Non-expansive mappings are strongly related to contractive mappings, but it is another world. It is another world, even if they are related. So I just want to make a short diagram. This will be Banach. These will be Cannon mappings. These would be Chatterjee mappings. These would be, I don't insist on them. These would be any others. And this would be almost contraction, then includes all of these and many others. And non-expansive are in this way. Of course, most of them, it could be here, maybe just a little bit there, but usually we have almost contraction which are not non-expansive. Again, non-expansive have some common parts. We'll see with quasi-non-expansive. They are included in strictly pseudo-contractive mappings, and these are included in the class of demicontractive mappings. Anyway, this enabled me to speak to one conference with the following title: Living in the Jungle of Non-expansive type mapping. And if I have time enough, I'll show a part of this jungle. There are a lot of kind of non-expansive type mappings. But essential, this class is extraordinarily important. And I would like to follow the same methodological approach. I mean, I did some, in the last years, by the way, maybe 10 years or so, I was most involved in algorithms to solve several problems for non-expansive type mappings. So this is why I want to show you how I was led to introduce a class of mappings I mentioned yesterday in the context of almost contractions. This means enriched mappings. And I would like to explain how it happened to me to see this, this class of mapping, this technique. And this is, I start by drawing your attention to this important concept in mathematics, extraordinarily important, the convex combination. All of us are familiar with the concept of convex combination, but for sure, in many chapters of mathematics, it is underestimated in the sense that we use convex combination, but we don't point out its relevance. This concept has a geometrical and linear algebra origin. It's easy. We know that the notion of convexity appears in geometry. Look, when it was first introduced in mathematics, in this almost 300 years, so in total 2,300 years before, he introduced the concept of convexity in geometry. Then the concept appeared in linear algebra as we use their linear combination. But it was a long process of evolution in essence, basically related to the development of analytical geometry, of algebraic curves, system of linear equation, and so on, differential theory of determinants and differential equations. You know, we use this concept of convex combination. Some interesting papers that I suggest is this one, a general outline of the genesis of vector space theory. It's from 1995, very interesting paper, and this nice book by Dorier. This it's in French, but it means that historical analysis regarding the emergence of the some elementary concepts in linear algebra. Of course, this concept was familiar to Euler, D'Alembert, Lagrange, Cauchy, Wronski. Wronski founded this this theory for differential equations, solving linear differential equations by linear combination, not convex. And the definition we know all is very simple. We have a subset of a linear vector space V, and this set A is said to be convex if for all vectors x, y in A and for any scalar lambda in 0, 1, we have this property. The convex combination of x and y belongs to A. So this Convex combination means that the sum of these two coefficients is 1. In general, we write it as ax plus by and a plus b equal 1. This is the convex combination. Fundamental concept in iterative approximation of fixed points, because 90% of the iterative methods are convex combination based. All are convex combination based. In the sense, we'll see we have such kind of convex combination of the terms appearing in an iterative method. So in general, we have this equivalent definition. We can have with many scalars, but their sum will be 1. These two definitions are equivalent. So we call such an expression like this a convex combination of the vectors x1, x2, xn. There are many fields of research in mathematics that use convex combination directly or indirectly. For example, this in fixed point theory, the relevance of convex combination was pointed out in this paper by my professor Roos, an abstract point of view on iterative approximation of fixed points, impact on the theory of fixed point equation. I would like to tell you that we always learn from our teachers. Always learn from our teachers. My beloved Professor Roos, he, at a certain moment, he said, Vasile, you are doing this, iterative methods. I said, yes, because I am a computer scientist and he realized these are important. So once he learned from his pupils, for his students, and he did a lot of very nice insight in these iterative schemes. Because in this paper, I do recommend you, is free on this journal, Point Theory. He put an abstract point of view and he pointed out the role of convex combination, and his generalization is very nice. I have no time to show you the concept. Above the convex combination he introduced admissible perturbation. He introduced, starting from convex combination, this admissible, maybe I'll have time to, perturbation of a mapping, which is the equivalent non-linear version of this linear convex combination. Then I draw your attention in real analysis. This paper, recent paper, bounding the convex combination of arithmetic and integral means in terms of one parameter and geometric means. What is exactly what I said yesterday. We have two mathematical objects, and if we compute the average, the mean of these objects, what it results in general, it's a better object. It's a new object, and sometimes, as I'll show today, we get a very important new mathematical object. Then, in system theory, in control, this paper, which seems to be written by some Indian mathematician, new hybrid active noise control system with convex combination. Directly in the title is mentioned the Then in operations research, in mathematical programming, also researchers are using the convex combination you can see of two different search directions of conjugate method and application to image restoration. Very interesting application. Then, numerical analysis. Again, numerical analysis methods to charged. Those will have a lot of work.
You are consuming our battery.
Yes. This is why I'm saying.
Because minds are working very fast. They have to switch from mathematics to computer, computer to mathematics.
Okay. Well, all right. So next, in optimization, I mentioned this paper by my friend and collaborator, Pum Kumam, from, by the way, Nutapol Pakaranang was my PhD student. He spent a lot of time at my university. And they did an interesting work by combining two different techniques and by convex combination to get a better algorithm to solve minimization problems. Then in statistics, you can see again by convex combination of Gaussian processes and Bayesian analysis for deterministic computer experiments. Probability theory and stochastics, again, semi-groove generated by a convex combination of two Feller generators. The same idea, to combine in nonlinear analysis, we'll speak now. So, in nonlinear analysis, I just remind you, Professor Murthy reminded you what is a non-expansive mapping. We should work now in a linear norm space, X, with norm denoted in this way, and a map T is a Banach contraction. We know already it's a Cannon mapping. We already met it. Chatterjee mapping, we already met it, and is non-expansive if this inequality holds. So, at the beginning, Kirk called this type of mappings which do not increase, how is the exactly, which diminished, I do not remember exactly its term, to refer to non-expansive mappings, in the sense that they do not expand the distance between X and Y by their images. So this is the key tool of some of these mappings. For example, Cannon mappings are quasi-non-expansive mappings. Also, Chatterjee are quasi-non-expansive, and we see what does it mean. So how I discovered what I call the enrichment of non-expansive mappings by convex combination. I was, when I wrote my book, almost more than 20 years ago, because it was the first edition in Romania published, and in Springer is the second edition. I was studying iterative methods for non-expansive mappings. And here the following concept we need. So we'll denote by T lambda the average, the convex average of the identity operator and the given operator T, which is non-expansive. We'll denote the fixed point set the same, similarly as now. And I just to tell you that I was contemplating for a long, long time these very nice results by Krasnoselsky. Krasnoselsky was an Ukrainian mathematician. Krasnoselsky means handsome guy. In Ukrainian means very handsome guy. But he was very big, he was a very tall, big guy and very handsome, really. He was a great mathematician. He did a lot of genuine results. Then Browder exploited the results by Krasnoselsky, and Ishikawa, a Japanese mathematician, he wrote a very important paper published in Proceedings of American Mathematical Society in 1976 related to non-expansive mappings. And look, what actually Krasnoselsky did in this year, 55, two remarks about the method of successive approximations. It was published in Russian, and what is interesting, this paper has been published exactly the same paper in a Romanian journal. I never I understood why. So exactly this paper was published in a Romanian journal in Russian, of course, again, but I don't know what happened. At that time, we were under Soviet influence, so maybe there was some agreement between the editors, and they published exactly the same paper in the Romanian journal. Okay.
Same type of results in SP Singh, BMAR, and Matkowski.
Yeah.
Matkowski's result is the same lemma what the SP Singh published in Journal of Australian Mathematical Society, and he published in Proceedings of American Mathematical Society. Same result, no change.
So, what is the idea? Krasnoselsky has shown that if T is non-expansive, that T lambda is also non-expansive. Very important. So, non-expansiveness is preserved by convex combination. And not only non-expansiveness, but they share the same fixed point set. So, the fixed point set of T lambda is exactly the fixed point set of T. And this enabled Krasnoselsky to construct an iterative scheme. And he noted also the following fact. This new operator, the average operator T lambda, is also asymptotically regular. This means that we have this property. The norm of the difference between T lambda the iterate n plus 1 minus T lambda iterate n tends to 0 as n tends to infinity. This means that it's asymptotically regular, but the map T is in general, a non-expansive map, is not asymptotically regular. So what is this? By using the average, the convex combination of a non-expansive map T, which is non-asymptotically regular, we get a map which is asymptotically regular. So, from the point of view of the fixed point theory, what does it mean? T lambda is richer, has larger properties than the original T. So exactly as I anticipated, by a convex combination of the identity and of the map itself, non-expansive, we get a map which has a new property, is asymptotically regularity. And this asymptotically regularity is extraordinarily important because we'll see, I don't know if I have on the next slide. No, I don't. So what is this? In general, xn plus 1 Picard iteration associated to a non-expansive map does not converge. Or even if it converges, it does not converge to a fixed point. But this new map, which means 1 minus lambda xn plus lambda t of xn, this converges to a fixed point of f. This was the main idea behind this convex combination. So we enriched by a convex combination. So this can be seen on the following simple example. Again, a simple example. Look, this map T 1 minus 6 is non-expansive, has a unique fixed point, but Picard iteration does not converge. We can see immediately. We take the initial value x0a, which is not 1/2, the fixed point, and then we get an oscillatory sequence, a1 minus a, a1 minus a, and so on. So this sequence, it's easy to see, does not converge because it is also oscillatory, but the T lambda n plus 1 minus T lambda n of x0 is exactly converges to 1/2. So is the example that a non-expansive function T and each convex combination T lambda, its average mapping is asymptotically regular. I have here an example to show the difference between these two instances. Picard iteration does not converge, and what I call Krasnoselski iteration to Krasnoselski. I consider Krasnoselski was the first one to do this significantly. And we consider a very simple non-expansive mapping is the rotation of the unit disk. This means we have the unit disk, and rotation means we rotate with a certain angle. So this is the map T, rotation of the entire disk. And of course, the unique fixed point of this map is 0 because it remains fixed, and the others are not fixed points, and the Picard iterations associated to it does not converge. I illustrate it immediately, but the average map T lambda has this property, so it's asymptotically. So here it is dynamic example. So we take x0, and T of x0 will be here, Picard iteration. Then T of x1 will be x2, and it is easy to see that it will go continuously and will have no convergence to the fixed point, which is here. But if we use now an x0, this is rotation with 90 degree. to be easy to see what happened. So x0 is here, the fixed point is here, and the image of x0 is rotation with 90 degrees, an angle of 90 degrees. So this is x1 in Picard iteration, but for Krasnoselski, what we did, we take the average. Here is lambda, I forgot to put there, is lambda 1/2. Is exactly the arithmetic mean, the average. So x1 is the average of x0 and t of x0. This means 1/2 x0 plus 1/2 t of x0. Then t of x1 is this one. We rotate it 90 degrees, it's here. Now to compute x2, we take again this segment. The middle point is the next iteration x2 because it's the average of x1 and t of x1, and so on. You can see that x2 already approached near the fixed point, and tx2 will be this one, x3 will be this, and we can see that the distance decreases. So the distance between the points and the fixed points decreases and will go in this way in a spiral, and this will converge to x0. This is the graphical representation of this situation. So once again, fundamental property of non-expansive mappings. Non-expansive mappings in general do not have a fixed point, but under some assumptions, and this famous fixed point theorem by Browder, Gödde, Kirk, if the Banach space is uniformly convex, okay, we have Professor Veramani will speak about normal structure, the way in which Kirk worked on this theorem. We know it has a fixed point. Normally, we also know that in under certain assumption, this set is convex, and so on. Many information. But Picard iteration cannot be used to approximate, in general, fixed points of non-expansive mapping. So this was fundamental in the class of contractive type mappings. We have seen Banach, Cannon, all these Helmholtz contractions, we were able to approximate fixed points by Picard iteration, the simplest possible iterative point method. But for non-expansive, we should go further. We should consider more elaborate iterative schemes like this one obtained by a convex combination. So once again, convex combination of two terms leads to convergence. So now my methodological step. I told you when I wrote, I do wish you will write a book. Where writing a book is something disastrous for you. So work for years, lot of work. I read almost 1,800 papers. Can you believe this? Incredible. From them, I selected some 400. There were the basic literature. Then working, crazy. I'll not do this now. Hey, so working on these chapters, because I devoted in my book 2 or 3 chapters to non-expansive mappings, type mappings, all the time I had the impression something is very beautiful inside this theory. So after a while, 5 years ago, 6 years ago, I put myself this problem. Okay, if we are in the case of non-expansive mappings, this map T lambda, which is the average map, has some richer properties. What will happen if I use in a certain contraction condition, instead of T, the operator T lambda, the map T lambda. I said, what will happen? So it took me a while to put this into practice. So this what would mean? For Banach contraction, instead of T, we put T lambda. It's a new contraction condition. For Kanan, the same. We put T lambda instead of T. We put T lambda to Chatterjee, and we put T lambda in the case of non-expansive. Despite of this familiarity of mine with these conditions, I don't know why I started with this. I started with this. My first paper on this kind was this. And so I was led to what is called enriched non-expansive mappings. I published this in 2019, but it took me a while until I finished clearly. So the way I introduced this class of new class of mappings was the following one. So I said, okay, I used this condition I showed you before, and this is the definition. Sorry, this is the definition. So a map T defined in a linear north space in general is said to be an enriched non-expansive mapping, or B, to show the constant, non-negative constant B, enriched non-expansive mappings, if we can find a constant B such that we have this condition. This condition, in my opinion, looks very nice. If we take B0, what will happen? Not is exactly non-expansive mapping. So it's quite natural condition. But look, where it comes. It comes exactly from this condition after transforming and, how to say, hiding the idea from here. So this is exactly this condition where I denoted lambda 1 over B plus 1, and we get exactly this condition. So this means we have an enriched non-expansive mapping. So as I said, it's clear that any non-expansive mapping T is zero non-expansive. So apparently enriched non-expansive mappings are consist of a larger class of mappings. But we don't know if this is true. So I introduced this definition. I said, okay, what is this class? And the first point was, as I said, and I insist on that, examples. Is there any enriched mapping, non-expansive mapping, which is not non-expansive? And here is a very simple example. We take this interval on the real line, 1 over 2, 2, and consider this map. If you remember, I consider this map. This is, they are related. Here is minus, and here is division instead of, so 1 over x for all x. This is self-mapping, and T is not non-expansive. It is easy to show. By the way, I forgot yesterday to challenge you to solve the examples I presented, one of the examples at least, but maybe we'll have a kind of session for discussion and for solving these examples. T is not non-expansive because actually T is Lipschitz map with constant L equal 4. What does it mean? This means that we do this. It's easy to see that it's, and for our data, this is less than So it is actually Lipschitzian. It's not non-expansive. This is not less than x minus y or equal. So it is not non-expansive, but it is enriched non-expansive. It is not difficult to show that with B 3/2 we have this condition satisfied, and it has a unique fixed point. So here is the proof I mentioned to show that it is not non-expansive. It is easier to take x1 and y 1/2, and then tx is 1, ty is 2, and norm of tx minus t1 is 1, while the norm of x minus y is 1/2, and this is not true, it's a contradiction. So we have an example of enriched non-expansive mapping which is not non-expansive. Here is the proof that it is enriched non-expansive. I don't insist on it. You can see how we proceed. We consider the definition, and in the end we found that B should be greater than 3/2, so we can work with B equal 3/2 to get this property. So the first idea is that these two classes are independent. So what is the relation? It is clear that enriched non-expansive are here and non-expansive are here, because I've shown any non-expansive is enriched non-expansive, but here we have this T which is here and is not here. So this is the point. We already enlarged the class of non-expansive mappings. It is also independent of quasi-non-expansive mappings. If you know a mapping is quasi-non-expansive if its fixed point set is non-empty, and we have this condition with y a fixed point. So ty becomes y, and this is quasi-non-expansive. Quasi-non-expansive class is independent of non-expansive class of non-expansive mappings, in the sense that a non-expansive map or a non-expansive mapping which has no fixed points is generally not quasi-non-expansive, but any non-expansive map which has fixed points is quasi-non-expansive. And here is the proof. We assume T is quasi-non-expansive, and we get for the same, for x 1/2, the same contradiction. So the class of enriched non-expansive mappings, which includes all non-expansive mappings, is independent of the class of quasi-non-expansive and the class of non-expansive mappings. This class is quite large. This is a first conclusion. So all non-expansive mappings are enriched non-expansive. Some Lipschitzian mappings, as I shown, are enriched non-expansive. Some generalized pseudo-contractive mappings, it's a concept introduced in this paper by myself in 2002, and all Lipschitzian and generalized pseudo-contractive mappings are also enriched non-expansive. So, what is the main problem of fixed point theory? We have a space, a setting, we have a map, we have some properties for this map, and what are we interested to know? Sorry, if this map has a fixed points, and if it has fixed points, to approximate the fixed point. This is the problem I consider for enriched non-expansive mapping. So, to decide if the class of enriched non-expansive mappings is a class that have fixed points, and then if these fixed points exist, to construct an iterative method to approximate these fixed points. And to establish such results, I need the notion of a demicompact operator introduced by Petrichin. Petrichin, I think he's still alive. He should be over 95, something. He's of Ukrainian origin, but his family moved in USA. He was a very good collaborator of Browder. They produced very high-level mathematics. He introduced this interesting notion of demicompact operator to extend the notion of compactness for operators. And the notion we need it, we'll see, to get strong convergence theorems. We have a Banach space X. T is mapping. It is said to be demicompact if for every bounded sequence xn from this domain of T, such that xn minus txn converges strongly to x, there exists a convergent subsequence of xn. This is the definition. So once again, the demicompactness means for such an operator for which xn minus txn, if x is 0, this is related to the fixed point problem, okay, and it possesses a convergent subsequence. Here it is important to point out that some product of demicompact operators and the product of real or complex number by a demicompact operator are in general not necessarily demicompact. So this notion is very special. This was introduced by Petrichin in 1966 and was used in the approximation of fixed points of condensing set contractive mappings in 72. Here are some examples of demicompact operators. Compact operators are of course demicompact if we are in a Hilbert space and we have these properties, which are generally the first one called, if we are in a real Hilbert space, this is called strongly monotone operator, and these are such kind of operators are demicompact for these values of alpha. Compact operators are mainly involved in the theory of integral operators, integral operators being the most important, perhaps, example of compact operators. When we work with Fredholm integral equations, these involves compact operators on function spaces, and the compactness property is shown by equicontinuity. We should not insist here for our aim, it is not essential. So, other examples of such operators. Look, this is a simple example of a demicompact operator. This is, you can see it's an example of a contractive mapping. It is not continuous, it's compact. A demicompact, sorry, is not compact. So in the case of this space of sequences with the usual norm, then T defined in this way, I forgot to mention C is the usual orthonormal basis of L2. Then this map is an isometry, is demicompact, but is not compact. So the demicompactness is a more general property which is enough for the needs of our fixed point iterative schemes. I have here one convergence theorem for enriched non-expansive mappings. Read. We have a Hilbert space, so we work in Hilbert space. The definition has been given in linear norm space, but as I mentioned, the Browder-Gödel-Kirk fixed point theorem is in uniformly convex Banach spaces. Here we need, for our work with iterative schemes, the structure, the setting of a Hilbert space, which you know is a particular case of Banach spaces. So we have a Hilbert space H, we have a bounded closed convex subset of H, C, and T is an enriched non-expansive mapping, which is also demicompact in the sense of this definition. In that case, the set of fixed points of T is non-empty, is convex, and we can prove this convergence, important convergence results. For any given x0 and any number lambda, the Krasnoselski iteration scheme, which is a convex combination of xn and t of xn by lambda, converges strongly to a fixed point of t. Because t is maybe even infinite set, it's maybe an interval, even an interval, we don't know which fixed point, but in general, we know that for any x0, we'll get a fixed point. It's not denoted here. It generally depends on x0. On the starting...
Xn is weak convergence.
Sorry? No, it's strong.
Xn also strong.
No, it's strong because of this demicompactness. It's strong. But wait. When we drop out the demicompactness, we have only weak convergence. So this, when we have the same things, but this first result is a particular one. So at the beginning, I could prove this only for the case we have a unique fixed point, P, and then the Krasnoselski iteration 2 converges, but weakly to P. So demicompactness is essential to get strong convergence. This was the first result in Hilbert spaces in this paper. I go back because I did not put here. No. Okay, this was the paper, 2019, 5 years ago. Well, at this moment, what we can say about enriched contractions? We are here. We have enriched contractions, and for any map T, including mappings here, we know this has a fixed point, and we can approximate the fixed points by the Krasnoselski iterative scheme. But only in Hilbert space we have this property. In a Hilbert space, we establish this result. So next, I'll reach some other things, but at the moment I want to mention an extension of this result to Banach spaces from Hilbert spaces by a special treatment, and then together with my best collaborator, Madalina Păcurar, we did the same work for Banach contractions, and this is the paper published in 2020, devoted to enriched contractions, then enriched Cannon mappings, enriched Chatterjee mappings, and I spoke yesterday about enriched almost contractions, which is the general, including all these classes of enriched mappings. What else? In convex metric spaces, the convexity, we know it's a structure of convexity. I use the convexity in the sense of Takahashi, and we produce this class of enriched contractions, contractive mappings in convex metric spaces, and we are led to this very important paper. I mentioned at the opening ceremony about saturated classes of mappings and unsaturated classes of mappings. So, we did also enriched Chirich-Reich-Rus contractions. Then some collaborators of mine, Abbas and Anjum did his PhD only on enriched mappings. I would come back to this concept of saturated and unsaturated. Okay, we worked a lot, you have seen. We did a technique of enriching for Banach, for non-expansive first, then for Banach, for Cannon, for Chatterjee, for Chirich-Reich-Rus. And all the time, if you look into these papers, you'll see that we always shown that Banach contractions are here and enriched Banach are here. So we enlarged. But I produced a paper where the original class was strictly pseudo-contractive mappings. And I published it. And after a while, I realized that the enriched strictly pseudo-contractive actually is exactly this. Is not enlarging. Okay. At this point, I realized not any class of mappings can be enriched by this method. I mean, by doing this process, considering the T lambda instead of T, in a contraction condition, we do not always obtain some new results. And this pointed us to this concept of unsaturated and saturated classes of mappings. As I mentioned, I was inspired by the concept in chemistry. I was good in chemistry. In my first year of high school, I was very good. In Romania, at that time, we have high school 4 years. After first year, the best students were selected to follow an elite class. So a special class of mathematics was called. So I was selected for both class of mathematics and chemistry, but I've chosen mathematics. And in this class of mathematics, I had a teacher, a lady, we did not love each other. So it was something, so I did not study chemistry, just to survive. But the punishment for me was, in the end, I married a chemist. And you'll not believe, I don't know, maybe you have this in India too. We have some meetings after 10 years of graduating high school. Do you have? 10, 20 years to celebrate 20 years of the graduation and so on. And this is a very nice meeting of classmates and the teachers.
Alumni meeting.
Alumni meeting. So we had this. And first 10 years, 20 years, it was present our teacher of mathematics, a great teacher. And then he died, and to the third, maybe 30 years anniversary, as he died, the representative of teachers was exactly our teacher of chemistry. And I had very serious issues with her, very serious, during my third and fourth year of high school. Anyway, because of me. This was because of me. Anyway, during this meeting, I confessed to my teacher the story. I said, teacher, look, I was this difficult student of you in chemistry. I did not want to study chemistry, and God punished me, and I have a chemist as a wife. She said, I am very satisfied, because she knew my wife very well. My wife used to be a very famous teacher of chemistry in that area, and so she said, good for you, because you did not study chemistry in high school. So let's come back.
So now you have very good chemistry.
So I was inspired in calling this concept. So the problem was, after doing some 5, 6 papers, do we always obtain real, effective generalization of known fixed point theorems by using T instead of T? So this was the question. So this suggested this topic in this paper, and we can afford, I'll continue maybe, tomorrow I have maybe 20 minutes more. Well, the definition we introduced in this paper is the following one. We are in the setting of a linear north space. We have a class of mappings. This could be any of these. Self-mappings. And we say that a mapping T is C enriched or enriched with respect to C if there exists a lambda such that this T lambda, the average map, is in this class. So this means that for Banach, when C is the Banach contraction set, we have the enriched Banach contractions, enriched Canaan, and so on. And we denote by CE the set of enriched mappings with respect with this class. Now, obviously, C is included in CE because, why? For lambda equal 1, T lambda is exactly T. Because T is in C, it is, so we have this inclusion. For all, we have this inclusion. And now, the next definition is crucial. We have C, this set of mappings, cell mappings. If C equals CE, I mean there is nothing here, we remain at the same set of mappings, that this class is saturated class of mappings. Otherwise, this means C is strictly included in CE, then we have an unsaturated class of mappings. So unsaturated means that C is strictly included in this one. So for Banach contractions is a class of unsaturated mappings because we have shown there is an enriched Banach contraction which is not Banach contraction. So we have this property, and this is the map I mentioned as an example of enriched Banach contraction, which is not Banach contraction. So Banach contraction is an unsaturated class of mappings. which is this lemma. So in a Banach space, the class of Banach contraction, this comes for Banach. The class of contractive Banach mappings is an unsaturated class of mappings. We can improve. Then is this theorem I already mentioned. We have for Banach contractions this theorem, Enriched Banach contraction, sorry. It is the paper I mentioned. Enriched canon, the same. It's an unsaturated class of mappings because of this example. We have a map which is enriched canon mapping and which is not canon mapping. So again, we have this conclusion. Canon, here it should be canon, sorry. Yes, it's canon. This means the class of canon contractive mappings is again the corresponding result for Ka-enriched canon mappings. We see for this mapping we have uniqueness, we have method for approximating the fixed points, but I should not forget for canon mappings we have Picard iteration, so this means with lambda equal 1, but here we need Krasnoselski iteration to approximate the fixed points of fixed point. It's only one of canon mappings. Other unsaturated I mentioned here, all these are unsaturated classes of mappings. Well, I promised you a saturated class of mappings. This is the definition of strictly pseudo-contractive mappings. You can see that this includes the class of non-expansive mappings because if we have without this part, this is non-expansive, and this, of course, any non-expansive mappings is K strictly pseudo-contractive. This class of mappings has been introduced by Browder and Petrician in 1967. Very important paper, very important paper. And they introduced this class without saying how they constructed this condition. And look, after I published one paper about enriching. Where is this paper? No, I'll go back. I forgot to put here. Why? I forgot. I'll show you this paper. This is the conclusion. In a Hilbert space, the class of strictly pseudo-contractive mappings is a saturated class of mappings. What does it mean? If we take a strictly pseudo-contractive map T and we construct T lambda is also strictly pseudo-contractive, nothing else. So this is a first example of, what is the key here? The key is that the class of strictly pseudo-contractive mappings is nothing else that the enriched non-expansive mappings. So K-demicontractive, strictly I didn't see, I'm to the next type. I have time enough. So I shall go back. So why is this class saturated? It is proven in this paper, but I will come back to this topic tomorrow in more detail. The point is that the class of strictly pseudo-contractive mappings is coincide with the class of enriched non-expansive mappings. And I proved this. In Hilbert spaces, this happens. So because there is clear, Hilbert spaces. And what I discovered, actually, Browder and Petrichin, when they introduced this class of mappings, what they did? They exactly used the technique of enriching, but they did not show the kitchen, what is behind this. They just put this condition, and this condition is obtained. I was anyway happy that I rediscovered this technique in another way, maybe the same way they used. And the next saturated class of mappings is a very important class. K-demicontractive is, as I know, the largest class of non-expansive type mappings for which we can approximate the fixed points by iterative schemes. This is the largest class. And I'll have in the presentation tomorrow some diagrams to show the relationship between these classes of mappings. But for the moment, I remind you that demicontractive means this condition. You can see without this part is just the condition of quasi-non-expansiveness, because Y star is a fixed point of T. So any quasi-non-expansive mapping is K-demicontractive, but the reverse is not in general true. This class of mappings I did not include here has been introduced by two American mathematicians and by a Romanian mathematician independently, and this is quasi-non-expansive. So if we denote by C, DC, the class of quasi-non-expansive, of demicontractive mappings, and by C, Q and E, the class of quasi-non-expansive mappings, then we have this important result. In a Hilbert space, C, DC is saturated because this class is coincides with the class of enriched quasi-non-expansive mappings. And I'll close with the following story, because I don't have here. Unfortunately, I did not include the references. I'll show you tomorrow. I have here a very nice story. K-demicontractive were introduced by Higgs and Kubitschek, two American mathematicians, but under the name operator satisfying condition A by a Romanian mathematician, a friend of mine. He died a few years ago, a very deep mathematician and computer scientist also, in 1977, independently. And this is the definition by Higgs and Kubitschek, is this one. Professor Maruster considered, he transformed, he used to have in another expression. I'll show you maybe tomorrow. And it took 20 years that specialists realized that the two conditions are equivalent. And actually, Maruster was doing this before Higgs and Kubitschek. And now I have to confess the following thing. Professor Maruster has been celebrated when he was 80 years old. I was invited to give a plenary talk in his honor. And this was the moment I started to look deeply into the class of K-demicontractive mappings. And I read the paper of Higgs and Kubitschek. I read the paper of Maruster, and you will not believe the theorems are exactly almost the same, a little bit different. in the sense that the assumptions in Maruster fixed point convergence theorems are more relaxed than in Higgs and Kubitschek. And I had the following wrong impression. I said, okay, Maruster submitted his paper in 1974, 3 years, reviewing process, long time. For Higgs and Kubitschek, they published, this was published in Proceedings of American Mathematical Society, this paper. This one was published, now it's a very famous journal, Journal of Mathematical Analysis and Applications. But at that time, there was not put the submission date in this journal. So there is no submission date. Then I was quite, how to say, convinced Higgs and Kubitschek read as reviewers the paper by Maruster, but this was not true. Because Higgs and Kubitschek actually did exactly what Browder and Petrician did for non-expansive mappings, but they did for quasi-non-expansive mapping. They enriched quasi-non-expansive mappings to get this condition. Browder and Petrician enriched non-expansive mappings to reach the class of K-strictly pseudo-contract. And for me, it is clear. So there is no, these papers were really independent. So really independent. Maruster found this class of mappings starting from an application problem, very interesting application problem in mechanics. And he was trying to solve this problem, a system of nonlinear equations, very big, 8 equation, nonlinear equation with 6 unknowns. And he was led to consider operators which are discontinuous because a demicontractive mapping is not continuous. A quasi-non-expansive mapping is not continuous in general, and he needed such a general class of operators, and he introduced this class which is exactly the same. So, to close this session, I want to stress on the fact that exactly the same idea. Anytime when we go deeply into a notion, into a result, into a definition, we can find some way for us to escape in a direction, new direction of research. So this should be done, but this requires a lot of work, hard work. This is what we should do, and not always. I know some people in my country, very good mathematicians. One of them worked 30 years of his life to an open problem, Riemann conjecture. So he did nothing. So he was trying to solve this problem, which is he did not succeed. But he was honest. He was doing this very seriously. It was a very difficult problem. And I end with a story. Do you allow me? Okay, I have 6 minutes to tell a story about an American mathematician. He is a famous Romanian American mathematician. His father was a teacher, a professor of mathematics at university, and his son said, no, I've been never a teacher of mathematics. I don't like to be a professor. I'll be an engineer, like Banner. And he went to engineering program. He finished engineering, and after a while, he realized, mathematics it's more beautiful than engineering. Let's try to do a master degree in mathematics. And he enrolled for a master degree in mathematics. This is a very nice story in Notices of American Mathematical Society some years ago. And he went to this program and he enjoyed very much. But one day, he was late in the class. The professor, their professor wrote on the blackboard at the time some problems, maybe 8 or 10 problems, I do not remember exactly. But he told students, he was not in the class at that moment, look, this problem, let's say number 6, our research group is working on it for 20 years, and we could not solve it. It's very difficult. So, but you should consider. And this guy, he entered the class, he had written all these problems in his notebook, and he went home and he said, this is homework. And he started to work and did, and when he reached this problem, he tried, he missed 1 week the classes, and after 2 weeks he came to his professor, he said, Professor, I'm very sorry to be late with my homework, but look, it was a problem which was very extremely difficult. And professor said, which one? He said, this one. Ah, really? Let's see. And he read, and he said, ah, you just did your PhD dissertation. This is true story. Because he didn't know this is a so difficult problem. So sometimes it's good to not know this and to work on the problem. So this would be the introduction to the next lecture when I speak about iterative methods for non-expansive type mappings, which is my concern in the last 10 years or so. So I was involved in constructing iterative algorithms for some classes of non-expansive mappings, not necessarily enriched, but I'll speak also on some enriched. So please question if you have.
Yeah, thank you, Professor, for very deep results in this session, and most of the iteratives he has covered, iterative methods, and his recent research in 2020, 2021, that also he discussed a lot. Especially the demicontraction, Demicompact, that and in Hilbert, the beauty of the Hilbert space is in non-linear space we don't realize the weak convergence, but when you enter into the Hilbert spaces, so then because of that inner product you can understand that what is the weak convergence. Might be many people who are not teaching functional analysis, so they may not be aware of even properly the weak convergence part. But weak convergence is a very good property, is a mild of course, very good property, and working particularly on such kind of property is a challenge also. Few people like T.L. Hicks, about he was talking about. I think I have seen more than 6 to 10 papers of Hicks, and his papers are with Whitefield also. Some of the papers in fixed point theory he wrote in Whitefield also. Some of his papers are, I think, Professor S.P. Singh from Canada. He also wrote with him. So very nice results here. What the professor was discussing about, I was actually interested with weak convergence, or is there any mechanism that the weak convergence part, how it is converting to the strong convergence, or strong convergence is there. So this part you know very well that, okay, because this is in PG curriculum also, MSc, there is a section also where you will go through the weak convergence part, and you can understand that how a book can be written, how a research paper can, good research paper can be written, and like byproduct petroleum products, you know very well that how such things comes out and finally you have the lot of paraffins. Okay, this is also the part of chemical engineering. So if you have any question, so
sorry,
you can ask.
I forgot to tell you, I want to apologize. Yesterday, today, and tomorrow, I am responsible for the accreditation of mathematics programs in my country.
Yeah,
So I have some meetings I missed, and I excused Professor Veramani yesterday and today the same. I have meetings for this activity, and I'll not be able to be here in the afternoon because 3 o'clock here is 12 o'clock in Romania, so I have exactly the agenda with these meetings. But on Thursday, I'll be available all the afternoon in case we can interact, we can have some discussions, deep discussions. I apologize for this. Is my activity, administration activity there.
Yeah, I have one book of Springer. Professor yesterday night he has given. Those who are interested. So just you give your names to Dr. Uma Devi Patel, who is here, okay, or one of my student is there, Mr. Adarsh Tiwari, okay, any one of them. So I will ask him what could be the charges from the outside, just in Koni village. You can visit Koni. Once you walk after 6, really is beautiful. Almost 10 kilometers area, no need of even the light of a car or any vehicle. It is so beautiful. You please go through such places also. Those who are from the outside also and believe in visiting some religious places. There is a place, Ratanpur. Okay, because I don't know whether I can find any time for you people to take for a visit. Because visit means at least I need 5 hours, right? And 5 hours sparing means one day. For me, I feel now difficult. Be serious, okay? And this evening, we are after the Professor Vermani's second lecture, okay? So we are organizing one interaction session with the faculty members of our department, okay? You can interact. Those who are available here or guest house, wherever you people find, but better is here only. So those who are available here, all the names also I mentioned in the schedule. So you please go through and along with them you can have the interactive session. Even those the PG students, they have also some curiosity because most of our PG students are outsiders. They are not from the locals of Bilaspur, few of them only, mostly outsiders. So they are residing either in Koni or some 5 kilometers away from this place. So they can also attend because this time won't come again. So I don't say that, of course you need some rest to understand or something. So in such cases I say that I always give one example of the cattle also. You see the cattle, what the cattle does, whatever the food is available, so available food grazing, okay, without thinking that what is the stomach size. And the stomach size is full, stop eating. And then go to the home and after the taking water, etc., sitting comfortably and thinking very nicely. So that is also the one technique to at least grab the knowledge. I don't say you can understand very well all the things, but at least you can grab the knowledge. Okay. So tomorrow after the professor's lecture, I will talk about the weak contraction type issues. What some Central European people or like he was referring the Professor Billy Rhodes did. Okay, his contribution is also marvelous. So we shall discuss all such things. Some of my contribution is also there. Few things I have done. So I will discuss all such things also. Okay, that will be on tomorrow, second half. Okay. So now this is the lunch time. If you have a no question, so lunch time is for 1 hour. So your lunch will be served over here. So thank you for your kind attention and your patience. Thank you, Professor, for your very nice, informative and impressive, and I can say excellent lecture. So we should clap.
Not out. Okay.
Friends, settle down please. Had your lunch? How was it? Huh? Same menu. No, menu. Same curry they repeated. No, quality is fine, but I requested them to change the curries. So no change. So okay, we will. There are some biscuits, you can have it. Okay, nothing should be left from here. Everything is. Yeah, you have to finish. Otherwise, we don't allow you to go. So, good afternoon, everyone. Half session over. Half session left. With us, Professor P. Veeramani from IIT Madras, and he will have two sessions. In session 1, he will speak about fixed point theorems for contractive type mappings and cyclic contraction mappings. The second one is the role of multi-valued fixed point theorems in the study of existence of Nash equilibrium points. So these are the two titles. One is related to proximity points, okay, cyclic maps, and other one the Nash equilibrium problem. So as Professor rightly said, yesterday he was talking about, in mathematics there is no Nobel, so it is unjustified with us. We do lot of work, but we have no Nobel Prize. Is there any conspiracy, sir? You have any news for this?
Nobel Prize is there.
No, Abel I know, Abel I know, but Nobel I don't know.
Yeah, maybe.
So field medal is there,
Yeah,
by International Mathematical Union. Those who are willing to attend Philadelphia 2026 ICM, you can apply, and those who are who have obtained their PhD after 2018, they can also they can apply for travel grant, ICM travel grant. I don't know whether they have extended or not. 20th of November was the last date, okay, what I applied. So you please, those who are, okay, Rashmi is there or not? No. So my PhD scholar, she got Brazil ICM travel grant to attend ICM at Brazil. I think it is 2018 maybe, 16 or 18. So you can also apply for the same. After some time, for Nepal, Professor Jha is the main person. Okay. So because Nepal is also included and they have given some special privileges for ICM. So I thought Jha is there, some people are here. When they see Murthy, they will provide me the travel grant, but they have not provided. So for Indians, there is another also, that is the NBHM's travel grant. Most probably you can get the time, within 6 months, I think it is possible to get the PhD, so you can apply. For this, you, Pushpalata Sahu, all of them can apply for that grant. NBHM will announce once again. But they need very good SCI papers. SCI is mandatory, okay? So you can apply. Age restriction is there. I think that is below 30 or 28 years. So you check your age also. So now with us, Professor Veermani, he will start with the contraction type mappings. And as professors always talk about the Billy rods, you can, I think those who are from the fixed point theory, 1977 paper, Proceedings of American Mathematical Society, that is 225 definitions, right sir? Actually it is 25,
yeah,
but they are numbers they are comparison, they made it, comparison of various types of mappings, that is the title of the paper. And he revisited also in contemporary, and several times he has written. So you can refer those papers. So I request Professor Veermani to continue his lecture today. Thank you,
thanks
Professor.
again, Professor Murthy. So welcome back. Maybe first half an hour we will spend whatever we left yesterday. Actually, we just started Jones lemma and what is called reflexive Banach spaces. These ideas we will be using tomorrow when we discuss fixed point theorems. Mainly today also Professor Perende has discussed some results related to non-expansive map and other type of non-expansive map. Will prove the main importance theorem proved by Prouder, Kirk and the same time in 1965. That will give the proof so that you will know the how we use the concept of little advanced compared to contraction. So that we will recall what is essentially compact. Compact in some other topology induced by the norm, that we call it weakly compact, that we need, that we will recall. And then Jones lemma is very important. Okay, before that, yesterday any questions? If you don't ask, I will ask. So then you will have to answer. Any questions? Any doubt also okay. Whatever we discussed yesterday, if you have some doubt, you tried and you could not, then you can ask. Some exercise, we left us some small things we did not discuss, we left it as an exercise, correct? For example, okay, this we discussed. Again quickly, F from close interval a comma b to close interval a comma b, a less than b is a continuous function, continuous. Then what is the conclusion? It has at least one fixed point. So then we used what we need is continuous image of a connected set is connected. Other is what we know as a consequence, what we call intermediate value theorem. For that what we to define another map G from close interval a comma b to R as G of x equal to either x minus f of x or fx minus x for all x in the domain. To make it simple, yesterday we took it close interval 0, 1. See, many times, sometimes actually the beginning, students may feel easy to fill close 0, 1 in close interval a comma b, but proof is exactly same. So then what we did, our aim is to find at least one x such that fx equal to x. That x may be a or or B or in between, it may be anywhere. Suppose, that's how we took case 1. Suppose f of A equal to A, then we are through. F of B equal to B, we are through. Otherwise, what it means? Suppose, that means we are assuming f of A not equal to A, f of B not equal to B. What does it mean? Where is f of A? It is a, see, what is the importance of the self map also we should realize. See here, A, forget about now, this closed interval, A, B to here. What is f of A not equal to A? And where f of A belongs to? F of A belongs to closed interval A comma B. And f of A not equal to A means f of A is strictly greater than A. Somewhere it may be, if you are writing doesn't mean that it is less than B. Anywhere between A and here anything right side. That means what? What is f of A minus A? F of A. So this is positive. And f of, sorry, this is whatever G of A, correct? G of A equal to this. And what is f of B minus B? Again, B not equal, f of A not equal to this. This cannot go to right side. Similarly, your f of A cannot go to left side. That is self map. Image of each x in the domain, fx again in the same domain. So, then not equal hence this. Now what happens? F of B less than B. So this is at one, that's what G, this is our map G. At one point it is negative, at another point positive, 0 is in between. Hence we get an x in the domain so that Gx equal to 0. Gx means fx minus x, 0 means fx equal to x. That's why sometimes given to prove result, how we get the motivation is through examples. See the example, using the example we'll get an idea whether we can do this for a general. Even as I told, Prower fixed point theorem, first proved for unit ball, then for any compact convex subset of finite dimensional nonlinear space. Then Fowler proved for infinite dimensional. Even not only each is very important. Later Kakutani proved, that will come in the next lecture, proved for multi-valued map. Again, what is called Tikhonov. He proved it for, some of you may be familiar or may not be familiar, what is called topological vector space. If it is a compact convex subset of a topological vector space and f from K to K continuous map, yes, it has a fixed point. Even that has been further generalized for multi-valued maps and many other directions. Okay? Okay, this is one thing. Any other, like this symbol, any other doubt you have? Whatever we discussed. Any doubt? Okay. So first I will start Jones lemma. You remember yesterday we just recalled to use Jones lemma. What are the first? We have a non-empty set. Our set is non-empty. Just okay. We start with a non-empty set, which we call it capital X. Capital X here, non-empty set. And we have a relation where What do you mean by relation? Relation is a subset of which one? X cross X. So relation, if you want, call it R. It is a relation. It is a subset of X cross X. Meaning is, we don't mean proper subset. It may be set inclusion. Whenever we mean subset, including we use with this as, understanding. A subset of A means X in A imply X in the other set also. Then this is a relation. That's what we know that. Even we can say that 1, 2, 2, 3 is a subset of R cross R. It is a relation on where? R. It is enough to have a subset. So what type of relation? Is it reflexive? No. Question is whether this relation defined this way. See now, whether this relation is reflexive? No. Question is whether it is reflexive or not. We did not, I do not know what is transitive, not defined. Right now, okay, reflexive also we are not defined. What is reflexive? Each element in the domain. Domain is what? R, set of real number. Each X is related to itself. Even for example, any real number, 1, 0, 2, root 2, whatever may be, it is not related to itself. Here, what do you mean by 1, 2 belongs to R? Here, this is our R. 1, 2 belongs to R. Then we write 1 less than or equal to 2. Okay? Here, alright? Any doubt? Okay. So now I will include just for some, you see the Y, 100 also there in the set R. Now 1, other way, right? 100, 1. 100, 1 belongs to R, imply what we write under this notation? 100 is less than or equal to 1. This is not our usual relation on R. The relation which we have defined the way 100 is less than or equal to 1. So instead of writing order per xy belongs to R, we write x less than or equal to y. Sometimes they write different notation, they write x related to y. This is what we write in place of that this. Or some other symbol also we write. In fact, using the symbol less than or equal to will give later to define upper bound, lower bound, least upper bound, greater, everything will become easier. Like in R we are familiar, the set of real numbers with our usual less than or equal to relation. Okay, now we have set X is a non-empty set, less than or equal to is a relation on X. What is less than or equal to mean? That R xy belongs to X related to Y, meaning is X less than or equal to Y. Okay, R is there. Order per xy belongs to R means R, the set R, subset of X cross X. Then we say that X less than or equal to Y. When we say reflexive, for each X in capital X is less than or equal to X. That means X is related to X for every element. Then only we say it is reflexive. Transitive means it is conditional. Reflexivity no condition. Whatever may be the X should be less than or equal to X. whatever may be the real number, x less than or equal to x. So like that. Now transitive conditional. Suppose x, y belongs to the domain x, x related to y, that means x less than or equal to y, and y less than or equal to z, then x less than or equal to z, conditional statement, transitive. Next is symmetry. Yes, okay, what do you mean by symmetry? Like usual, if again conditional, if x related to y, then y related to x, that is symmetry. Partial order, we don't like symmetry, where y equal to x, mean x equal to y, then x related to y, x less than or equal to x, that is comes from reflexive. Otherwise we don't want symmetry. In a strong sense, we are not saying not symmetry. The relation is not symmetry means what? There exists a pair xy such that x related to y, but y is not related to x. But what is anti-symmetry? Anti-symmetry is same as not symmetry? No. Very good. That is, here again, if x related to y and y related to x, that means symmetry between x and y. Then what cannot happen? They cannot be different. That's what x related to y. That's why similar to R we compare x less than or equal to y less than or equal to x imply x equal to y. That's what we call it anti-symmetry, essentially again like against symmetry, even for one pair when they are distinct. Then such a set we call it a set capital X. We have set capital X and a relation, that relation R, then we understand that xy belongs to R means we write x less than or equal to y. So we just write that x less than or equal to x is our set. The relation, using this we got this. These relations satisfy these three conditions: reflexive, anti-symmetry and transitive. Then the set x together with that relation is called a partially ordered set. This is also important. Later I think Professor Berende is going to discuss, or Professor Murthy, partially ordered metric spaces are there. They will define on a metric space some partial order relation, then using that they will discuss some fixed point theorem. Here our interest is, we have a partial order set. Now see, because of this relation notation, when we say an element, say x naught belongs to a, naturally the whole world is now, we do not know anything about other than x. X naught belongs to x. We have a set like a non-empty insert. We write this as a partially ordered set, just we write pro set. Capital A non-empty subset of x. Then x naught belongs to capital X is called or said to be on, this I am writing for upper bound, if and only if, we all know what is the condition. When we say x naught is an upper bound for what? Upper bound for the set A, if and only if, conditional again, x belongs to A imply x less than or equal to x naught, that's all. That's what similar to, if you use some other notation, you can use like R, then what we will have XR, y or XR, X naught, like that. It will not be getting that idea immediately. Now upper bounding we know like in R, x less than or equal to x naught for all x in the domain, here our for all x in the set A, then that x naught is called an upper bound for A. Again upper bound need not be like in R, need not be in the set A. It may be in A or it may not be in A. So that is second condition. Then everything, then we have here again C, we take non-empty set, subset of X. When we say this is a chain or a totally ordered set, again see, from both we get the idea. Totally ordered means you give any, why we call it partially ordered? Like we saw the example 1, 2, 2, 3, where 4 and 5 are related. 4, 5 is not in our R. That means we cannot say 4 related to 5 or they are not related, but they are in the capital X. I mean that we have to check, that was not a partially ordered set, the given example. So our set here, it is a partially ordered set. Okay. Then when we say it is a totally ordered set, total ordered set means what? XY belongs to that set imply either XY order for XY belongs to our relation. So in our notation, X less than or equal to Y or Y less than or equal to X or equal already there. The X less equal to X is there. So we don't imply X less than or equal to Y or Y less than or equal to X. But can both happen? That's what, that can happen only X equal to Y. That means what? Suppose X not equal to Y, then only like that case we write strictly less than. Anyway, we don't use strictly less than right now. It's clear? Then such a set we call it a chain or pardon? Yeah, okay. There in real analysis whatever we have, either for given any element either x equal to y or x less than y, and that here we just here on any partially ordered set, not just in R. So we have so we'll use the term chain or total ordered set, the name. So what are the things we have here? Partially ordered set, and if we have a non-empty subset, we know when an element from X is an upper bound and when a set is totally ordered. So this we know. Another somewhat, I mean for a beginner, not that immediately you will get is what is called a maximal element. Similarly we can define minimal element. See, yesterday we gave example. Maximal element. It is not maximum. Maximal, even in R or this, we don't say it is maximum element, maximal element. So we will use that. For that we do not require any subset. X is partially ordered set. X naught belongs to capital X is said to be a maximal element of capital X. Definition means either you write if or if and only if same. When we say X naught is maximal element, that's at the topper in mathematics, topper in physics, topper in chemistry, all are maximal element. But topper in maths, not related to topper in physics like that. So among the related people he is the best. If they are, so that's why we say if and only if x belongs to x, x naught is smaller. It is like x naught is inferior to x. So marks obtained by the x naught and x less than or equal to x means that should they are equal, no problem. So other only this topper means x naught less than or equal to x imply
X not equal to X.
X not equal to
This implies X not equal to X.
x not equal to x, x not equal to x.
X0 equal to X.
What?
X not. This condition implies X not equal to X, then X not is called maximal element.
No, this imply, see this is maximal. See maths one student topper is got 90 marks. Suppose somebody, we can say some other x, x naught is less than or equal to x. That means what? X should have got more marks than x naught, either equal or more. But only one topper means that such thing cannot happen. That's what we say. X naught less than or equal to x imply.
X not equal to X.
No, what is the natural thing? Can anyone else, topper got 90 in maths. Can there exist another topper with the same 90? We assume that they are all distinct. No two different students will get same marks. We will assume just for simplicity. So they are not equal, but x naught less than or equal to x means what? Not equal but strictly less than. Then the marks obtained by x is more, but we call it x naught is maximal, we want to call. So such things should not happen. That means what? What is the relation between x naught and x? X naught should be x naught is not related to any two element in mass are related. One topper in mass not related to topper in physics. If they are from they are already related, given they are related. It is given that x naught in capital X, when we call x naught is a maximal element mean, suppose conditional, if there exists an x such that x naught less than or equal to x, whether that is possible. Possible or not? MSc somebody, see x naught less than or equal to x means x is superior. Yeah, but maximal means above him nobody is there. See, that's what we gave the lattice diagram sometime called, if you have mass like this. One student here, the topper is here, above him nobody will be there. Some other physics, here and here not, they are not related. So he is topper, above him anybody will be there? Nobody will be there. That means what? X naught less than or equal to x should imply what is the relation between x and x naught? They are correct. Equal, very good. X equal to x naught. I mean x, okay. So x in x naught less than or equal to x imply that x equal to so x equal to x naught, no contradiction. They are equal mean reflexive is there. Okay. That's why this is somewhat you have to little spend some time. if you are listening first time, maximal element, because some of you might have not seen Jones lemma, things like that. It will, so there is any doubt? Right. I mean,
For some x belongs to x.
no, conditional. Suppose their x is x, such that this condition is satisfied. Whether there is at least one x, x equal to x naught. X naught is already less than or equal to x naught. Other than that, there will not, x naught less than or equal to x should imply x equal to x naught. It's clear? So this we call it maximal element. Maximal element may be more than one. For a partially ordered set, that's a vector space, all of you studied, no? Vector space. Suppose R2. Can you tell what is a basis for R2? 1001. It is a basis. Any other basis? 1, 2, 2, 3, any number of, any linearly independent set containing 2 elements. They are all maximal linearly independent set in that sense. What, at least you heard about maximal linearly independent set? A is a linearly independent set. Capital B is a not linearly independent set containing something. Okay, that's what we are going to see. These are all, every vector space has a basis, non-zero vector space. Zero vector space also has a basis. Some books they may not like empty set, they don't like mean. Empty set also a basis for span of empty set. Span means what? Span of a set A means it is a, correct, it is a subspace, smallest subspace containing span A, containing A. What is the smallest subspace containing empty set is single, that zero element alone. That element, but that is not linear. So empty set is linearly independent in that sense. Span of empty set is singleton 0. Hence, that basis containing empty set basis. How many elements are there? No element means 0 element. That's why the 0 space contain, it has a basis, dimension is 0. That's why 0 space dimension 1. One non-zero element means dimension will be greater than or equal to 1. That's why there also we will prove in finite dimensional vector space. We can start with any non-zero element. Suppose x1. Consider span of x1. If span of x1 equal to the whole vector space V means span x1 equal to whole vector space V, x1 is non-zero means linearly independent, then it is a basis, dimension is 1. Suppose span of x1 is not equal means proper subset, then we will get an x2 in V not in span of x1. x2 in V, x2 not in span of x1. Then x1, x2 will become, we can easily prove that linearly independent. Then x1, x2 linearly independent, consider span of x1, x2. That may be equal to V if it is equal to V, x1, x2 basis, otherwise continue still finite we can go. But infinite dimensional we cannot do that, so for that we need Jones lemma. Using Jones lemma we can prove that, start with any linearly independent set inclusion. A, we have a collection of linearly independent set containing one particular linearly independent set, then A subset of B means A less than or equal to B, like that. Then we can prove using Jones lemma maximal linearly independent set exists, that will be our basis. But our main aim here is fixed point theorem. So this exercise, use Jones lemma to prove that every vector space has a basis. Okay. Now what is Jones lemma? We have a non-empty set, then we have a partially ordered set. Then take any chain, you can assume non-empty chain. Any chain, suppose every chain, we keep going, we cannot go beyond the root. Every chain should have an upper bound. Once going like that, it should have an upper bound. If every chain has an upper bound, then it will have at least one maximal element. At least one maximal element. That is what Jones lemma. That is we call Jones lemma. You want any hint to prove vector space as a basis? You want hint, I will give, otherwise you try yourself. Which way you want? Pardon?
Can be done.
Okay, very good. Okay. Now, in fixed point theory, how we are going to use, just I will indicate because I stated, tomorrow we will discuss that. In fixed point theory, some type of compact set we will assume that X is a non-linear space or even assume Banach space, capital K, non-empty, it is even assumed that compact convex subset of X. In fact, what we need is, instead of compact, something called weakly compact will assume. That I will explain. K compact convex, T is a norm from K to K. That means T of K, subset of K. X belongs to K, is Tx belongs to K. We have this condition. It is called a self map. Then our aim is, there exists to prove, or aim or to prove, there exists X in K such that Tx equal to X. This we want to prove. Can you think of some minimal set similar to maximal set? If we have a partially ordered set, suppose every chain has is of upper bound, lower bound. If every chain has a lower bound, then it will have a minimal element. Can you think of a minimal set having this property? K is a subset of our Banach space. Even Banach space or metric space set doesn't matter. It is any set even, okay. Later in the proof we need all those things. Can you get a smallest minimal set? What is the condition? Say, let us say F is a minimal set. That means what type of set you have? So that X belongs to F imply Tx belongs to F. X belongs to F, F is subset of K. See, we want that, this we will call it script F, set of all F subset of K. What is important is empty set should not come. Some other condition later we will assume. This. Whether this is going to be our partially ordered set. Script F. This is non-empty. This collection script A. Script F is a collection of subsets of K. An element F belongs to K means F should be non-empty and it is invariant. I mean the T restricted to F is invariant, meaning X belongs to F imply Tx also belongs to F. Can you give, then what is our aim? What is our goal? We want to find an X such that Tx equal to X. So what should be that F?
F singleton set having
So we have to prove that use Jones lemma to get a minimal element. Then use some other additional condition. The minimal element alone will not be sufficient. Something else in non-expansive, proved by Prouder, Coke and Kirk in 1965. They first, in fact, Prouder proved in 65 for a Hilbert space, assuming that K is a closed, bounded, convex subset of a Hilbert space, T from K to K non-expansive. Non-expansive are explained in the morning also. That means norm of Tx minus Ty less than or equal to norm x minus y for all xy in the domain. Okay. Then under this condition, K closed bounded convex subset of a Hilbert space, T non-expansive map. Then there exists x in K such that Tx equal to x. That Prouder proved. Then at the same year, Key improved his own result. That is something called what is uniformly convex. For example, finite dimensional uniformly convex is simple to, you have here, see what is in R2. Have you seen the square or rhombus like this? What is this thing? Units R2, what are the norms you are familiar? R power 2, Euclidean plane. Order pair x1, x2 or xy. Order pair x comma y. What is the Euclidean? Another name for Euclidean is Pythagoras. In fact, how you get the idea of the usual distances, use Pythagoras theorem. Just if you see that symbol quickly, we want spend. Suppose this order pair xy, we want to define this is our distance between, in this case x0 will assume. We call it xy like this. Then this distance is y minus x, 0 will be anywhere else, correct? No, sorry. 2 point, we will assume that this is 0, 0 or this is xy, then this distance will be x, this will be y and this will be root of x. That comes from Pythagoras theorem. Similarly, any instead of this some other x, this distance is the plus this, that's what the root of that what is so called Euclidean metric. That metric you are familiar. Or norm of order pair xy equal to positive root of x square plus y square. What is L2? This we call it L2 norm. What is L1? Norm of order pair xy, suffix 1 to distinguish, equal to norm x plus norm y. Norm x plus norm y. And L infinity norm or maximum, that is maximum of mod x comma mod y. There the unit bore all like this, say square L infinity or L1 rhombus type. What is there? The problem is, if your unit sphere is like this, square type, that means x is here, y is here, norm x equal to 1, norm y equal to 1, x not equal to y also, norm of x plus y also 1. Such things should not happen in a finite dimensional non-linear pair. If it happens, that means norm x equal to 1, norm y equal to 1, x not equal to y, in fact the midpoint, norm x plus y by 2, strictly less than 1. That's what our unit sphere, like our usual Euclidean norm, root of x center at 0 radius 1. here any point x here, x means other pair, x1, x2. If you want to call it x1, x2. Another point here, then midpoint where it will be? Midpoint will be strictly less than 1. Not only midpoint, if you take any point in between, later we will see now for equivalent other than the end point. Such spaces, finite dimensional, this will be equivalent to uniformly convex. We will define later. That is called uniformly convex Banach space. I mean non-linear space also, uniformly convex Banach space is more important. That implies it is a reflexive Banach space like that. But like L1, L infinity will not have this property, even finite dimensional, because you take the point on the norm x equal to 1, norm y equal to 1, some x not equal to y, still it can happen that midpoint also on the unit sphere. So they are not strictly convex. This happen in a uniform way. That is called uniformly convex. When we know closed set, all those things we know. So here there is we have the topology which we call it topology induced by the norm. That is the usual topology. Another topology which we call it T tau omega tau w, whatever tau omega we call it. This is we are going to call it is the smallest topology on x having some nice property. What is that property? See now we have this is x. F belongs to x dash imply f is linear and f from where to where continuous? X to x with respect to this norm to R. What is R? The usual mod xy is distance between xy is usual metric on R. D of xy is mod x minus y. There we are not changing. R the same. This is what continuous. Now we want to give another topology A to define a topology on x satisfying this condition, satisfying a topology called, that topology we want to call tau omega. Then this it should be for every, for all f in this condition should be satisfied. Okay. This implies we want smallest such topology that exists, that is called the weak topology on x. Now we have a topology which we call it tau omega. We have to prove such a topology exists. That topology is called weak topology on any non-linear space. Now we can talk about compact. Compact with respect to this topological space x comma tau omega. Compact in x tau omega is called weakly compact. That's what we need. Okay, this clear? Okay, can you say what is the relation between tau prime and tau? Tau prime is some topology. Okay? On x such that f from x tau omega to R continuous. Can you say anything? Can there exist larger topology? Even it can be. Can you give some very large topology? Large topology useless for us because we are searching for a smallest. If we
discrete topology is
already, suppose the tau prime is discrete, whatever may be the function, you take any open set, inverse image is a subset of x, topology is discrete topology, means every set will be open, then this function will be, whether any function in particular, this type of f belongs to x prime also, it will be continuous. So, but what we want is, that's such a, we want the smallest topology, so that whenever the topology tau dash is such that for every f in x prime, x with respect to tau prime to R continuous should imply tau omega is a subset of tau prime. In particular, it will be subset of tau also, tau norm, because there also it satisfies f belongs to x prime in already f from x tau norm to R is continuous, but tau, that means tau omega will be subset of tau norm. Okay, so this much enough, at least to have an idea. This we will be using. That's why to use Jones lemma, we need this compactness. We will be using compact. What is important is compact if and only if it has a collection of closed set which has, correct, using some intersection property. Compact if and only whenever it is a collection of closed set which has finite intersection property, then it is compact. That we will be using, that type of thing. Okay. So, it's fine. Any doubt? Please, this is very important, at least to, even if it is not very advanced, but that's a, but this is a part of metric topology. Though not very advanced, but at the same time not only Cauchy sequence and convergence. Okay. Any doubt? Okay. Okay. Now this will come back tomorrow when we discuss about non-expansive math. Now again to justify the topic, we have already discussed. Due to time, I will restrict to, we have X complete metric space. Complete metric space. Every Cauchy sequence in X converges to an element in X. A comma capital B non-empty closed subsets X. Almost like contraction, we will define T from A union B to A union B satisfying the following condition. T such that means it satisfies the following condition. 1, T every element in A goes to element in B. Every element in B goes to element in A, and distance between T we are using, no? Tx comma Ty less than or equal to, there X is K, 0 less than or what is important is less than 1, non-negative and less than 1, K time. Okay, here you have to put some condition. Which condition you like to put? For all xy in A union. Suppose I write for all xy in A union B, will it be a new result? Suppose you write this condition for every xy in A union B, then what is A union B? A closed subset of a complete metric space, or A closed B closed, mean A union, finite union. A union B is a closed set. So in place of X, say our metric space Y equal to A union B. Subset of a metric space also a metric space. Closed subset of a complete metric space is complete. So A union B is complete. Correct? A union B is a complete metric space. So T from A union B to A union B, they satisfy for some K 0 less than or equal to K less than 1, satisfy this contraction. Then what it says? It has a, that is nothing but Banach contraction theorem. Okay? Okay. Now also it is going to be Banach contraction theorem. Okay? And tell that why for all x in A, y in B. See here, when xy both are in, xy both in A or xy both are in B, we cannot write this. Only distance between tx, ty less than or equal to k time distance between xy, only when x is in A, y in B. It is nothing great, just it is in a way, some simple way of, we should not use, okay. Right now we do not, this condition is there. What is that? So many times we discuss Picard's iteration. What essentially we use? Start with any x naught from A. I mean x naught from the domain. It may be capital X if it is mapped from x to x, in this case A union B. X naught from A union B means x naught is in A or in B. Then what is Tx naught? Suppose x naught is in A, Tx naught is where? B. Tx naught, T of T, that we call it x1, like Picard's iteration. X naught belongs to A, T of x naught we call it x1, that is in B. Again T of x1 will be in A, call it x2. T of x2 will be x3, call it, that will be in B, and so on. So that means what? X naught, we are iteratively, if we define n, xn may be either in A or B by induction. Assume that we are able to define x naught x1, assume that we have defined x naught x1 xn. We should be able to define xn plus 1. Xn is in A, then xn plus 1, T of xn will be in B. It is in B means xn plus 1 A. So we can define inductively. So what type of sequence we got? x2n is in A, x2n plus 1, all the odd term will be in B. Even term x naught, x2, x4 all in A. What type of sequence this? Using this condition. The defined sequence xn. What type of sequence? That is nothing new. Here no absolutely new. What type of sequence xn? Pardon? We use the given condition. What? How you prove Banach contraction theorem? Cauchy. How you prove Cauchy's? First you will start with distance between
xn minus
xn and
less than xi.
no, that will come little later. To start with, distance between xn.
xn minus 1.
Very good. Xn and xn minus 1 or xn, xn plus 1, anything. Can we use distance between xn, comma xn plus 1. Xn is where? Either in A or B. Suppose xn is in A, then xn plus 1 will be in B. But what is xn by our definition? X naught is any element, T of x1 is T of x naught, x2 is T of x1, like that. So again xn is nothing but T of xn minus 1. Xn plus 1 means T of xn. So distance between xn and xn plus 1 is equal to distance between xn, distance between T of xn minus 1 comma T of xn. Xn minus 1, y is in A means xn is in B. This xn minus 1 B mean next will be in A. So we can use this condition. Less than or equal to k time distance between xn minus 1 and xn. Again proceed less than or equal to k square, then you will exactly Banner contraction theorem. Less than or equal to k power n distance between x0 and x1. That's it. Then we will use, then we will go to distance between xn and xm. Less than or equal to distance between xn and xn plus 1 plus distance between xn plus 1, xn plus 2 up to assuming m greater than n. Then use the, I mean like each is less than or equal to k power n, k like that. Then k power something is geometric series, converges. Then you will prove that distance between xn and xm is Cauchy sequence. Exactly same idea like proving this. That is the sequence xn is a what type of sequence? We can prove that xn is a distance between xn and xm will tends to 0, we can prove. See, once we get that any letter in, whether it is Banner contraction or Kannan type or Chatterjee or many other things, what ultimately will prove is, will start with any x0, will start with any x0 from the domain. See, we will start with x0 from the domain, then x1 is tx0, x2 is tx1 like that. Then what we are going to prove is xn plus 1 xn is less than or equal to some k, that's a k time distance between xn, x1 less xn minus 1 like that. Then k square time and like that, some k power something, yeah, n minus 1 or okay, n minus 1 something this. Then here it is less than or equal to some constant. Then this we cannot this state, then we use this is inner. Once you prove this is k okay, like k power n into some fixed number, not variable. Then using that we prove it is a Cauchy sequence. Then that converges, whether it is Kannan type, Banner contraction, we do the same thing, immediately we will be able to prove this. Then that will become a Cauchy sequence, completeness, it converges, then that point is a fixed point. Only what is important is, as Professor Verinde mentioned many times, what is the beauty of that is not the proof. Kannan, when you prove this result, the important thing is it's a it is not a continuous map, but proof is essentially same. Even the Chatterjee also essentially same. Many other things, again that inequality you have to use properly. So idea is same, but still they are all important and has nice application. That's why Professor Verinde has given many nice algorithm and many interesting examples. So here we prove that in our case, what is our x2n belongs to a n02, x2n belongs to a, in this case, with this condition, maybe x2n belongs to a, it belongs to A, x2n plus 1 belongs to B. What type of sequence xn? This is x2n is nothing but subsequence, x2n plus 1 another subsequence. What is the original sequence? It is xn, it is a convergent sequence. Suppose xn converges to x, what will happen to the subsequence? It converges to the same point. So x2n also converges to x, x2n plus 1 also converges to x, that means x belongs to A
No, intersection.
intersection. In the beginning we don't assume that A intersection B is
Contradiction.
non-empty, no contradiction. That implies we cannot separate. Under the contraction condition, under this condition, this implies A intersection B is non-empty. Then once A intersection B is non-empty, you can consider T of A contained in B, T of B contained in A. What is T of A intersection B? Contained in A also, T of A intersection B contained in B also, T of A intersection B contained in A intersection B. Our vector, now our metric space is A intersection B. A, B closed, A intersection B also closed. So T from complete metric space. Closed subset of the complete metric space is complete metric. Now it is nothing but Banach contraction theorem we can use. So what is important thing here is, we don't assume that A intersection B is non-empty. Here our aim is to prove A intersection B non-empty, that's all. Fixed point existence is proved by Banach. We will then, motivated by this, suppose we have in single case like R2 itself, we will forget about contraction also, we will see. So this is 0, 0, x 0, y 1, 1, 0, 1, 1. A is this. What is A is? X coordinate set of all 0, y 0 less than or equal to y less than or equal to 1. Capital B set of all 1 comma y such that 0 less than or equal to y less than or equal to 1. Now I do exercise. Can you define a map T from A to B, B to A? Satisfying that condition, we cannot say the distance between T contraction type, because now they are what type of set? Disjoint. Suppose distance between Tx, Ty, suppose Rx is a K, 0 less than or equal to K less than 1, so the distance between Tx, Ty less than or equal to K times distance between xy, or x in A, y in B. Then of course they are assuming that R2 in this case, they are all closed subset of complete metric space. Under that condition, we have proved that A intersection B is non-empty. So, but here they are disjoint. Elements in translate, all are migrated from A to B. Okay, here A to B, similarly B to A, here we can define A to B or B to A. Then we don't want this condition forces for x in A, y in B, forces to, this will imply this intersection is non-empty. But this type of situation, can we expect a fixed point? Is it possible? We cannot expect. What is the next best thing? In particular, distance between A and B may be, it should include the original case. We don't assume that in general A intersection may be empty or may be non-empty. Okay? We are assuming even closed compact set under suitable condition, distance between A comma B may be positive. Here positive. Then it is almost like a contraction type. So this will, after T we will come and discuss. Distance between Tx, Ty minus, I will write 0. K time distance between xy, anything wrong? 0 is nothing to write, no? 0 we can write, no? nothing wrong, no? Can you replace 0 by distance between A comma B? This is a contraction. Suppose distance between A comma B greater than 0, then what we see from this, we subtract distance between A comma B. So this distance between Tx, Ty less than or equal to, minus this distance between Tx, Ty minus distance between A comma B, sigma is 0. Then this is less than A times between xy minus distance between what should be A comma B. That in particular will be 0. So this is 0 imply usual contraction. If they are separated, then this we call it, what we call it, cyclic contraction. In fact, the earlier one we just informally we discussed with Professor Kerr, and he felt okay that we can, because that time these people have not used this concept T of A subset of B, T of B subset of A, like contraction type. There itself they call it cyclic. That's what many have done. But what we realized is they can be separated. So motivated by this concept we introduced in 2006 jointly with my student Anthony Eldred, and that appeared in Journal of Mathematical Analysis and Application. The first one is with Professor Kerr and my another student Srinivasan, that appear in Journal of Fixed Point Theory, which comes from Cluj-Napoca. Okay, after T we will continue. Come with a doubt or you can ask.
Any doubt?
Yeah, feel free to.
Yeah.
That's it. If you are not asking, then I will ask.
Yeah, definitely. Then we sit and this time. See, beauty of this is Professor Kerr and I met most of the stalwarts in mathematics. I am fortunate in that manner. So even I met Billy Sims, as well as Kirk also, and Billy Sims and Kirk are very good friends. Kirk is from US and Billy Sims from the Castle, Australia. So actually here the issue is you have fixed points. Okay, so they are discovering the fixed points where normally you say that the distance between 2 points is 0 if they are coincident points. But here they started with the distance may not be 0. Right? Then only such condition has come, the proximity, something like that. Yeah. So that manner actually the cyclic contraction has come, like you have a map, the image of A is in B and the image of B is in A back. Okay. So that way this is highly interesting, and recently one of my student who awarded PhD, her whole thesis is with the proximity points.
Oh, that.
And you are the god of that thesis because a lot of your all fundamental papers are used in that. But one thing is, for every research paper we have given the applications, either in differential equations, integral equations, or some other. Not in game theory, we have given the applications of the proximity point. So this is also a good thing. Normally we are very much strict to only the fixed point that Tx is equals to x, and we say that is a fixed point. But what happens when Tx is not equals to x? Your assumption is from Tx not equal to x, right? Yeah. So, any question? Yeah, that's why. So A intersection B, A union B, okay. A intersection B is shrinking.
Yeah, that time Kaifon was the problem.
Yes, Kifan. Yes. Ah.
68 or 69, that will be.
Kifan has, Kifan has introduced that, and and I think he will now speak about the multi-valued maps and the first paper in multi-valued map in specific journal of mathematics. So that multi-valued map, Pacific Journal of Mathematics appeared first
Not
time.
your paper.
No, not yours, not yours.
Original.
No, original paper that appeared in Pacific Journal of Mathematics might be 1967,
I don't know.
around,
Yeah.
around, around.
That has been-
Yeah, yeah.
Giving the
See,
motivation, not very advanced level.
yeah.
How to get multi-valued map to use in the existence of non-significant.
No, first of all, you have to understand what is a single valued, what is a multi-valued, and what do you mean by a normal map also. Because you should have the very good clarity. That's why I said you come with some sort of mind that, okay, professors or our experts are going to speak about such things, and out of those things, what I know and what I need to know. That is very important. So this kind of curiosity is important, and that you have to develop. See, not necessary you do research and obtain a PhD degree. Everywhere you require some sort of research. Even you do any job and some conspiracy is going on against you, how do you identify that this conspiracy should be shutted out? You need some research. Okay? So I think our food is giving very good sleep to everyone, right? Few of you are sleeping very nicely. Our food is giving very good sleep. So I will say that food should not be that level. It should be little bit reduce the quality. So anyway, if no question, I think we can check out whether tea is ready or not, and we shall meet at 4 o'clock. Okay? Thank you. Banach fixed point theorem in 1922, if you look into that, you will find that before the Banach, there was no such conditions. Okay? You see the Brouwer, there is no such condition. Brouwer is very simple. Simplest, I can say that theorem, that you have the fixed point, that you have a continuous function from a closed interval to the closed interval, and this continuous function is have a fixed point. Okay, they are not talking about the uniqueness. That's the difference only. So Banach has given the uniqueness, but if you look into the hypothesis of the Banach, you will find that that way Banach is a very strong hypothesis, strong results, lot of. Its own contraction is loaded, or I can say that inbuilt continuity. It's a strong. Apart from that, one inequality, again a strong. After that, providing the uniqueness, means just for the sake of the uniqueness, lot of hypotheses assumed for this theorem. And after that, you see everyone is running behind the contractions. And like the Chirik's contraction, the maximum possible combinations, that was taken care. Okay. So now the professor is going to speak on this. This is over, sir. Contraction part is completed.
Just 5 minutes.
5 minutes. Okay. Okay. So after I think a few more information he has to pass you people. So after that he will talk about the multi-valued mapping, right? Multi-valued mapping, no? Yes, multi-valued mapping, and its fixed points. So as I said, single valued, multi-valued, set valued. They are all looks alike, but they are all different. So I think definitely you are going to talk such things. So he will speak about this also. Make a distinction of all such things. Wherever needed, you go to the room and home and do some homework. Okay? And may I ask you, how many of you are interested after 5:30 for a interaction? Please raise your hand. If you are interested, then only I will request my colleagues to stay over here. Otherwise, their work is also very hectic. So how many of you wants to stay? Because anyway, we have one open session, 2 hour session, maybe on Thursday. I think it will fall in Thursday. Any one of you? No. Okay. No issue. So yeah, maybe because some heavy classes. So I request Professor V. Mani to continue his lecture, and this will last till 5:30. In between, I finish some of my work and back to you people. Okay? Thank you. Okay, Professor.
Yeah, thanks, Professor Murthy. Okay. So, sir, before any doubt in whatever we discussed yesterday, today, till now? Any doubt? So that's why you are not asking doubt, so I will give some more homework as Professor Murthy suggested. Yeah.
In precisely merits of this contraction, cyclic contraction.
Merit of?
Cyclic contraction.
Merit is?
In precisely way.
Yeah. The cyclic contraction, when there is no fixed point. That's it. Later this again tomorrow we'll talk. We have two non-empty. See, it's like this. One, this wall is a plane. Opposite side is another wall. All one, that's it, either this wall or two disjoint sets. This is A, this is B. Elements in A, even this is enough. Instead of T from A to B, need not be cyclic even. If some cases we can assume T of A subset of B, T of B subset of T of A. In fact, originally we started this work in 1997 with my student Sadiq Basa. Later he also has done lot of work in this area, ACTA, science, math, Seagull. And then 2000, Journal of, again with both with my student, Journal of Approximation Theory. That time we are considering A and B to non-empty sets. T is a map from A to B. And under what condition one can find an X in A, there exists X in A such that X in A means Tx is in B, such that distance between the point X and Tx among all the points, Tx is the nearest point to B. That's why this is less than or equal to distance between A comma B for all small a in capital A, B in capital B. This is what our aim. To achieve this, we are trying to find a point X in A, so the distance between X and A equal to distance between A comma B. If this so, this is less than or equal to distance between A comma B for all A, because this is nothing but infimum or greatest lower bound of distance between A comma B, A in A, B in B. So we give sufficient condition, under what condition we can find an element X in A such that distance between the point X and Tx equal to distance between the set A comma B, that is the minimum distance. In particular, for closed set suitable condition A and B equal to 0, that case we will get distance between X equal to Tx also. It will include fixed point, but more generally if there is no fixed point, what is the next best thing? That's why we have two vertical lines. Then we find a point X, the Tx, that is the nearest. See, for example, this. We give the vertical distance, we will give other type also. See here 0, 0, 0, 1, 1, 0, 1, 1, vertical line. If we take a point here 0 comma X, that goes to 1 minus 1 comma 1 minus X. So like that. So similarly we can even A to B alone, let us say. Similarly if you want to, we can define B to A. This is clear? Vertical line. A equal to the vertical line joining 0, 0 and 0, 1. Capital B, vertical line joining 1, 0 and 1, 1. Map is this way. 0 comma X goes to, because it should be in B. X coordinate 1, Y coordinate is 1 minus X. Which is the best, nearest, see you want application you want to see. All the people from A move to B. Some person I want to go, which is the nearest among all. Who will get, you want, can there exists a point X in the domain A, such that the corresponding, the new name for X is Tx. So the distance between X and Tx is minimum among all the distance between A comma B. So which point will we work here? We can see geometrically. What is the distance between first A comma B? Usual metric. See, distance between A comma B means if you take a point here, you have to find all the, one point here, then you have to take the infimum. What is the infimum? Pardon? 1. So which point in A, distance between that point 0 comma X and T of 1 comma 0 comma x and 1 comma 1 minus x equal to half 1 by 2. So there exists a point 0 comma half whose image is again 1 comma 1 minus x, again half, 1 minus half, that is this midpoint. So we get this point, the mid, this is the nearest. So that is our motivation. So there are under what condition? Later this that's what we, even that whatever we call cyclic contraction, that we introduced in 2006, which appeared in Journal of Mathematical Analysis and Application. In fact, earlier that we will discuss non-expansive map jointly with Anthony Eldred, myself and Professor Kirk.
But sir, that paper is not available online.
Which paper?
You say Kirk and you.
Kirk and me, that paper? Cyclic or?
Cyclic contract.
Oh, that is maybe that Cluj-Nabucco or that journal of, maybe we have to ask Professor Merende from their university. In fact, that we were discussing, informally, we were discussing some other things related to best proximity.
That paper have a good number of citations.
Yeah,
but the paper is not.
That is very simple. That is many that's the main thing is the second version that we appeared in 2006. Yeah. Yeah. Okay. If you have thing, if you send, I don't have this, I don't know now I will have this because I don't have, now use only cell phone on email, but I can ask my student or somebody who can send it. Okay. So any doubt about, okay. We will discuss related things in the, tomorrow we will discuss about, now one lecture mainly meant for best proximity points, that time we will discuss in detail. Okay, before that, some contraction, some very simple exercise, only you have to use triangle inequality suitably. X complete metric space or metric space doesn't matter. T from x to x, 0 less than or equal to k less than 1, first condition, distance between Tx, Ty less than or equal to k time, distance between xy for all xy in x we know. And see, alpha strictly greater than 0, we are not telling less than 1 or anything. So that distance between x comma Tx plus distance between y comma Ty for all x in A, y in B. This is very trivial. Okay, suppose only this condition is satisfied. T is a map from a metric space x to a metric space, no completeness, nothing. Such that for some alpha positive, distance between Tx and Ty less than or equal to alpha time distance between x comma Tx plus distance between y comma Ty. Suppose it has a fixed point. We do not know whether it has a fixed point or not. Suppose it has a fixed point. What can you say about that? Can there exist more than one fixed point? Under this condition. Can there exist more than one fixed point? Proved by contradiction, or what will happen if Tx equal to x and Ty equal to y? Suppose Tx equal to x for some xy in x, Tx equal to Ty, you write it. What will happen? This condition is satisfied. Tx is a fixed point, means this is 0. This is 0. That means distance between Tx and Ty 0. Tx is Ty. Why? Tx equal to Ty. Tx, x equal to Tx 0, y equal to Ty 0, this is 0, Tx equal to Ty, will it imply x equal to y? When it will happen? Or it is? Pardon? If it is 1 1, it is okay. If it is 1 1, then that case this T in Tx Ty. For what xy? Whether you have to put some, suppose this is true for any xy, correct? We have put any restriction on x and y? No. Suppose let us fix one x, say x naught. Fix x equal to x naught. Fix x equal to x naught. Okay, then what happened? Distance between Tx and instead of y equal to, okay, x, we will call it O, okay. Fix x naught equal to y. Then distance between Tx and Tx naught is 0. If distance between Tx and Tx naught is 0, but what we assumed already, we forgot something, x and y are, even we don't require this. This we are, what we are assuming that x and y are fixed points. So fixed point means x equal to Tx, y equal to Ty. Hence don't go for distance between Tx, Ty equal to 0, but because Tx equal to x, Ty equal to y, distance between xy is 0. That means x equal to y. Okay. So this condition will imply Tx equal to x, Ty equal to y, imply x equal to y. If they are, then it will become unique fixed point, whatever may be the, it may be a contraction map or Chatterjee or some other map including non-expansive. Suppose T from K to K a non-expansive map, under some condition it has a fixed point, in addition to that it satisfies this condition, then also it will give you a unique fixed point. That's what if you observe that exercise, contraction case also you will get this. Same thing, second exercise, many things, distance between Tx dy less than or equal to k time distance between x and Tx plus y and Ty means that is Kannan map, that alpha equal to k, but go to x comma, also discussed y comma Tx for all xy in x. Then this also, suppose this imply, again this implies Rx is alpha greater than 0, so that distance between Tx, Ty less than or equal to alpha time distance between x Tx plus df, just use the triangle inequality. So do simple exercise, okay. That's it. If it is contraction also we will get this condition. Kannan map already there, even it is Chatterjee. So most of the uniqueness this will be, alpha need not be 1 or anything, alpha is just any positive number, okay. Now you manufacture, that means I have manufactured X unit, I am going to, this will go to market and they will decide where it goes. If the player select X from, second player select Y from N, then both will get some income. income may be positive or negative or 0. Okay, that we call it. So, in a natural way, we have a function f from m n to r. This is called payoff function. Payoff function for player 1, and g from m cross n to r, that is called function for player 2. This clear? See, in general it may be, if necessary, we can restrict the codomain also, that is different. Right now we allow them R, some real. What is the meaning of this? What do you mean by f of xy? What is the meaning of g of xy? What is the meaning of first f of xy? You will select first player has selected x from his strategy set. He cannot take anything different from outside, he cannot go. He has to take x from m at a time, x, one element. He has selected x and inform the second player, I have selected x. Now you select any other y, take anything which will give maximum profit. So what f of xy at a time, that will not decide the maximum. That is if the first player select x, second player select y, f of xy is the income for player 1. G of xy is income for player 2. If it is loss, many times in game thing is a profit, they will go for loss, minimize the loss. You want maximum or minimum? Your choice. You want to maximize the profit or minimize the loss? Pardon? Minimize the loss, very good. Okay, we want to minimize the loss. That means what? So that is, so what we, first player has selected x, then the second player, he can select any one strategy from where he can take, from his strategy set, n, such that if he select this y, x already he has fixed first player, then his profit should be minimum. Loss is minimum. That means what? This is for second player. You are talking about second player loss are this. That means G, first player already selected x. If it is maximum profit, means this criteria are equal to this. Loss should be minimum, so less than or equal to, correct? F of x comma y, then it is correct. That means the second player have not, how do you know? That select some y which we do not know. See, among all, see, let us say m equal to, symbol came, toss a coin, 0, 1. Chess mean, okay, whatever the thing, or rolling a dice, 1, 2, 3, 4, 6, 7, 8, whatever may be, or symbol. Toss, 0 comes mean, I will get this amount. 1 comes mean, like what are the thing? First player can get either 0 or 1. So what are the m cross n? m cross n, in this case n also will assume that because both are tossing coin, unbiased, it will not show either 0 or 1. So what are the things? 0 0 0 1, this set is non-empty. Okay, that means this is a subset, this we call it T2 or, okay, I will change the notation if necessary, or we call it T1 of X. This T1 of X is a subset, under suitable condition we will assume that it is non-empty. We will assume that it is a non-empty subset of N. This clear? Any doubt? So same way now routine. Now the role changes. Now what will second player will select a strategy Y and he will inform the player 1, I have selected Y. Now it is your choice. I mean each month or each whatever one occasion I will do, then you have the freedom. Second time you give the freedom to me. That is the understanding. So now second player Y has selected N and Y goes to, now it is the choice of first player. Set of all X from his strategy set M, say that again you want to increase his maximum profit. So F of which is fixed, Y is fixed, second player has fixed, he cannot change. No, now it may give me loss, I will change the mind, that is no cheating is there. So second player has selected Y, second player, first player can select anything, okay, so that if this will give the maximum profit, that means F of X comma Y, what is that? Now profit, we change to maximize, this is you give the maximum profit, greater than or equal to F of A comma notation, variable, they are also used A, that A variable from N, this variable from M, A comma Y, very good. For all A belongs to M. Again we will assume suitably, this we call it T2 of Y, again suitable condition we will assume non-empty. Okay, my job is over. If you are able to follow this much, so we are through. It is any doubt, you please go through 1 minute, see that you are able to follow. Not any thing difficult. Any doubt to anyone? First player select X, then second player from where he will have to select? He is going to select from, if we select anyone from the T1 of X. So in a natural way, now define a function T from M cross N to M is a non-empty set of rules or strategy set for player 1, N strategy set for player 2 or set of rules. So M cross N, we know that set of all order for xy, so that x belongs to M. This, which is a subset of M, T1 of x or T2 of y, which is subset of, pardon, T, first where it is, this T2 of y. That's why I would have, even if you want, you would have used this is T2 or T1, doesn't matter. Okay. So this is T2 of y, T2 of y here, subset of m. This is subset of m, this is subset of n. So T2 of y cross T1 of, this is T1 of x. This is a subset of m cross n. So that's it mathematically. Suppose m is a subset of R, n is a subset of R, then m cross n is a subset of R cross R. That means m cross n, Ni is compact, m is compact, convex, n compact, convex, then Tikhonov's theorem. Okay, m cross n also compact, convex. Compact and also you can prove it convex. Okay, convex is correct. Okay, so we can under suitable for us right now we don't worry about all the things. M subset of R, n subset of R means m cross n subset of R. Suppose m is subset of a non-linear space X, n is subset of a non-linear space X, then what will happen? Shall I erase this? Okay. Suppose M is subset of X, a non-linear space, and a Banach space, Hilbert space, anything you take. Say a non-linear space. N is subset of a non-linear, same non-linear space will take. Then M cross N is subset of X cross X. Can you define a norm on X cross Y? X is non-linear space, Y non-linear space, then X cross Y also a product norm, any one, there are many ways to define. You have seen, third semester MSc students have done functional analysis, they have done or not yet? Oh, at least norm by this time, you know, no, product norm, you are familiar, not yet familiar, mean I will tell. Norm of order, what is the simplest way? X is in X. Then what we know? X is a non-linear space, mean for each X in X, we have a length of X. X goes to norm X. Norm X we know. X in X mean norm X we know. Y is also in X mean norm Y we know. So using norm X and norm Y, again to we want to define a X vector space, Y vector space, X cross Y vector space, we will assume over R. Okay. Then in a natural way we can define norm of order per xy. What is the natural way? Even if you are not done, what do we feel? Norm of x plus norm of y, or maximum, or many way, norm of x power p plus norm of y power p whole power 1 by p, 1 less than p, less than infinity, like that. See, we are in a finite dimensional space, mean it doesn't matter topologically. Finite dimensional space, all norms are equivalent. Anyhow, what we want is, we have a norm on x cross x also. That means what ultimately we will take is, instead of m cross n, we let k equal to, let k equal to m cross n. Then T is a map from K to K, such that, now what we will tell, we will come back to this situation. K is a subset of m cross n. Then for each x in K, the image is, okay, now suppose some jet belongs to K, imply under this condition, T of jet is a subset of K. We assume that under suitable condition, T1x, T2y, they are all non-empty. That means the T of Here x means, that z means some order per xy type in our case. That means ultimately what we have, our order per xy goes to t of xy. That is, we call it t2 of x cross t1 of y, anything. So we have here image of each pair xy is a non-empty subset of that m cross n, non-empty subset. So that map we call it set valued map, or the sometimes also called multi-valued map. So that in a natural way, while doing M theory, we come to multi-valued map. We get in a natural, we get a multi-valued map. That is T from M cross n to M cross n is a set valued, I will write it set valued map. Sometimes they write it instead of m cross n, they write 2 power m cross n. I will assume that set of all non-empty subsets of m cross n. Notation only, so nothing wrong to say that T is a map from m cross n to m cross n, such that for each element situation we don't want. Now, what is our aim? What is our aim? You should not forget keeping what was our purpose. Our aim was, forgot, we have two players m and n, player 1, player 2. M set of rules for player 1, set of rules for player 2. And if the player 1 select a rule from his strategy set or set up from M, second player select Y, then f of xy is the profit for player 1, and the same time the same situation, g of xy profit need not be same. G of xy profit is, second player profit is g of xy. Then what is our aim? Maximizing whose profit? Player 1, you favor player 1 may be your friend. So I want to favor player 1, so let him, what is the situation here? Whether there exists a situation where both player will get the maximum profit. That is, let us say player 1 selected a strategy x0 and player 2 selected y0, then f of x0 y0 is the maximum, give the maximum profit for player 1, and same time to player 2 also. G of x0 y0 will give the maximum profit for player 2. So then to get x0 y0 naturally from m x0 from m. So now one neat. Now you do the work, and I hope you can come across. Now we have seen that we are talking about fixed point theory, at least. So x0 should belongs to where, y0 should belongs to where. See which way we have defined? First we define T1x. T1x we define set of all y from n, so that g of xy gives the maximum profit. Okay, that means what? If the y belongs to where? Y belongs to T1 of x. So if y belongs to T1x means y is here, then that will give the g of x comma a. This will do. But at the same time, if you select anything from this, it will give. But at the same x and y are fixed, or you call then g of x naught, key has selected y naught, then g of yeah, first player has selected x naught. Y is no, y naught is if is sorry. Yeah. Here it is. I will change the note here. Suppose we want to select x naught from M, y naught from N. Then this selection should give the maximum profit for both. That means x naught belongs to where, y naught belongs to where. You tell this. Yeah, you can take 1 minute. I mean even 2. Question is clear? If you understood the definition of how we define T1 of x and T2 of y, proof is over. Anyone? At least this, I want that one of, at least some of you should get. By this time you should have got. See, x naught, y naught belongs to, if we want such a x naught, y naught belongs to our domain. T of x naught, y naught. What is T of x naught, y naught? By our definition. Very good. T2 of y naught cross T1 of x naught. Very good. Now tell. Image of order pair x naught, y naught equal to T2 of y naught cross T1 of x naught, which is a subset of M cross N. Now can you, if there is a relation between x naught, y naught and this set, that means essentially x naught, y naught is one point, image is another point. When the second player will get the maximum profit? Huh? Very good. Yeah, then what is the meaning of that? Sir has written x naught belongs to T2 of y naught and y naught belongs to T1 of x naught. Very good. So what do you mean by this? See, I will write. See what you check what he has taken. He is giving the condition not belongs to T2 of y naught and y naught belongs to T1 of x naught. That means what? X naught, y naught belongs to T2 y naught cross T1 of x naught. This is equal to what? T of x naught, y naught. See, this is like together some z. This is some z. That means what? Z belongs to T of suppose order pair x naught y naught, it is an element of a non-linear space or R cross R, that we call it Z. So that means Z belongs to, so we want to suppose that this belongs to T of Z. So what do you mean by Z belongs to? For each element in the domain, the image is a non-empty subset, that is a multivariate map. Then our requirement is, suppose we get an element Z in the domain such that Z belongs to T of Z, then according to him we will verify. Then that Z will give maximum profit for player 1 as well as player 2. That means that Z equal to order pair x naught y naught, such a situation, if such a pair exists, we have to prove under what condition, what is the condition on the domain M cross N, and what is the condition on the payoff function. Then under suitable condition, yes, there exists a point order pair x naught y naught belongs to M cross N, such that order pair x naught y naught belongs to T of x naught y naught, and that gives maximum profit for player 1 as well as player 2, and that pair is called our starting point. That we call it now equilibrium point. That is introduced by Nass, I think either 51 or 52 somewhere, when he was like many of the MSc students' age. He was just 21 or something.
That might be called coincidence.
No, coincidence point is fixed point, and this is not coincidence point.
Saddle point maybe.
Saddle point is that. This is called, even that's one of the, many books on game, mathematical economics it has, that's what, as I told in the yesterday, Nass using Prover fixed point theorem. What is Prover fixed point theorem? Like M compact convex, N compact convex, M cross N is compact convex. Under suitable condition, F is a continuous, or we can assume lower semi-continuous or upper sufficient. So suitably condition on F, some continuity condition, that will give the map. Even one can use Prover fixed point theorem, that is more easiest is Kakutani. We can give a simple proof using Kakutani theorem, because in a natural way this is multivariate map. Yes. So for each X, the image is a multivariate map. What is Kakutani theorem? That was proved by Kakutani 1940 something later in the some Kakutani generalized Prover fixed point theorem to multivariate map, that to finite dimensional. What is that statement is? X is a finite dimensional non-linear space. You have to stress non-linear space or Banach space. Pardon?
When it computes, then we say
a finite dimensional, whether it is?
Finite dimension is always Banach or not.
Okay. So we have a finite dimensional non-linear space. So X is a, I will write this, will retain. X is a, like even R power n you take. Vector space over R power n type. T from x2, that's it, if you want 2 power x we can write, or that for each x, the image Tx non-empty, closed, convex is more important, convex subset of again x, correct? Because the domain, that's it, is better to write T from x to x, so that for each x in x, Tx is a non-empty, closed convex subset of X. So what we take in Kakutani 6-point theorem, the domain will not take the whole space. Suppose we take the domain the whole space, what will happen? Domain we don't, then under suitable condition it can have fixed point. It is a Banach space. Then we require a very, like even we have seen that R to R also. Even we have seen that closed, even R to R, X goes to X plus 1. Translation map. It is a nice isometry map. It does not have fixed point. So we cannot expect that type. So what we have is compact convex subset of a finite dimensional nonlinear space. K, non-empty always, compact convex subset of X, finite dimensional nonlinear space. T from K to K says that these are already compact convex. For each X, Tx is compact also we can say, because closed subset of the compact set is compact. Okay, we will tell even compact convex. So further for each closed subset of K, C closed subset of K. It is a subset of K also closed. Will it be closed in the original space? C is closed because K itself closed. Okay, C closed subset of K imply, suppose T is a map from K to K, single valued, or we call it F in this. Y belongs to K. What is F inverse of Y? Those X in K whose image is Y. So that Fx equal to Y. But here Fx is a set. Here it is a set. Then what we should have? Here F inverse of again, if C is a subset of set also we define inverse image of F inverse of C. How we define? Set of all X in the domain. Okay, domain, suppose domain came in, domain is K, so that only one element means that Fx equal to Y means what? That belongs to, Fx belongs to singleton Y. So here it is what? Fx belongs to C, all the three images. But here it is a set. So that is, it is Tx, that case what we say that, not in this case, we can, that is very strong. So we define this as all X in K, so that Tx intersection C is non-empty. Suppose if it is single valued, Tx single valued means Fx belongs to C. So this is called pre-image of a set under multivalued map. So C is a closed subset of K, then the inverse image T inverse of C is again a closed subset of K. And suppose whenever C is a closed set, inverse image of closed, if it is a single valued continuous map means what? Inverse image of open set is open, similarly equal inverse image of closed set is closed. Here if whenever C is a closed subset of K, inverse image is again a closed set, then that map, multivalued map, is called upper semi-continuous. It is not same as F from X to or lower semi-continuous upper, it is multivalued map. It is called upper semi-continuous. Similarly, whenever C is an open set, then inverse image is open, then that is called lower semi-continuous. See, this concept we can define more generally: X topological space, Y topological space, X goes to Tx, subset of Y, then inverse image of closed set is closed mean upper semi-continuous, inverse image of open set is open mean lower semi-continuous. If it is both lower and upper mean continuous. There are even we can say the what is called metric projection. Best set up all, if A is it depends upon the time I will give that example. Okay, now what is Kakutani theorem says is the domain K is what is the domain? Compact, convex, subset of a finite dimensional nonlinear space. T from K to K, a set valued map or multi-valued map, satisfying what condition? And again we are assuming that for each X, Tx is a compact convex set. We will assume non-empty compact convex set. Further, T is upper semi-continuous. Upper semi-continuous. Then it has a fixed point. Then there exists fixed point means then there exists X in K. Under that condition there exists X in A, X belongs to Tx. In our case that X is some order pair x0 y0 belongs to T of x0 y0, that is equal to T2 of x0 cross T1 of y0, like that. So now we are having here, for example, this clear? So that means under suitable condition we can use Kakutani. Almost we have done the proof of that. In fact, it is F is a Yasim even continuous function. For convexity we can lower semi-continuous mean for minimized case, upper semi-continuous maximized case we can assume that concave, like that. We want that our set should be T1 of x0, T2 of y0 convex set. So we will assume suitable condition. So that for each order pair xy, T of xy is a nice compact convex set and domain M cross N is compact. Under that condition this T is upper semi-continuous. Hence it has a fixed point by Kakutani's theorem. Now that implies, now x0 belongs to T2 of y0 implies x0, what is this imply? x0 belongs to T2 of y0 implies what? What is that? x2 belongs to T2 of y0 means what? What is? It will both. x0 belongs to T2 and y0 belongs to T1 of x0. So this implies f of x0 y0. Here it is here. Once an element is here, that gives the maximum profit. For whom?
For
Player 1 and similarly here player 2. That means this will give you, this is greater than or equal to f of, when we selected x0, if is that this will give the maximum profit. Similarly for G, that means this order pair x0 y0 will give the maximum profit for player 1 and 2, and that existence theorem comes from fixed point theorem of multivalued map. Later this theorem has been, Kakutani's theorem has been generalized in many directions. One of the, somewhere in late 50, I think National Academy of Sciences USA, Kyphon or Kyphon we call it. Again K compact convex, only we can assume Banach space or non-linear space. What is important there then is for locally convex topological vector space, and it is a multi-valid map. Again, for each x, Tx is a closed convex set, the map is upper semi-continuous, then it has a fixed point. Essentially it is a generalization, but it is not our simple generalization of, using some non-trivial, highly non-trivial. Kaifon, later Himmelberg, and much later even 1992, one Lassalle from France, what he did was factorize. T is a map. What is the image? Main thing is strong condition is convex. He assumed that T1 composition T2 type, more generally for N map. So each factor, this is T1 of T2x. He has assumed T1 of T2, that means T1 of y is convex, T2 of y is convex, but the composition may not be like something we sometimes if we do like this. See, suppose we have a square in R2. See, all the element goes to, let us say, here. Every year we fix it, compact, anything. So all the element from this set goes to here. That is T2 of x or T1 of, then here the nearest point. We will have a nearest point, this is called nearest point. Then what is the this will become, first it goes to here, then comes here. So like that. But individually what is, for each x, this is a straight line, which is a convex set. But if then for each element here, it goes to only one point. Again a singleton convex, but what is the image of a set? See, not T1 of, here it is T1 of T2x. This whole line. Then this will be T1 of some A, union A belongs to that set. Then that need not be a convex set. So that is a nice result he proved in 1992 in Journal of Mathematical Analysis and Application. I think there also he has given some application to, I think similar to.
Anyway, we cannot say convex union of convexity.
That's it. Union of, that's what exactly.
Is true. But
union, that's what here. Here the union of convex set, that's why it need not be, convex set need not be convex. But what is the beauty of that result is, each T1x is convex, T2x is convex. The original map, x goes to Tx need not be convex valued, but still it will have a fixed point. That is further generalization of this whatever.
this is only possible when one contains another.
Which one?
Is it possible the union part? One contains another. T1x is contained.
We don't have it. Then it will become only one set now.
Then they will make one set.
Then it is nothing but one.
Set.
Okay. So just to, because I is upper semi-continuous, I will just start with one example, which is the motivation for our next best proximity point also. Then with that we will stop. Even we will start with the metric space. A, capital A, non-empty, compact, convex subset of a metric space. We will write for metric space X mean X with D. See, we have a metric space X. We have a set A which is compact. to each point x, we want to find the nearest. So that's someone come from Bilaspur, so we want to, some communication tower, we want to fix. We cannot fix somewhere, we can fix outside, we will not like the radiation, all those things, so inside, no. But we select in such a way that that is the nearest to the city, not nearest to the, that way. What we want is, for a given x, find the nearest point from y, from A, that is, what condition actually it should satisfy? Distance between x, y, among, you take any point here, A, distance between x and A, x and y, x and this, all this thing. Among that we want to take the nearest point. That means a point y in A is said to be a nearest point to x, is said to be a nearest point to x, nearest point to x from where? From the set A, if and only if, okay, what condition you tell? Oh, I am not, I wanted to write something, so incomplete, you tell. What is the condition? Which is nearest? See, I am standing here. Who is the nearest to me from this group? Professor Dhananjay Gopal. Because distance from x and Dhananjay Gopal, x and this, among all the things. So that is the nearest. That means what? Distance between x and y less than or equal to distance between all other points. To that set A. A only we have called, okay, for all A. If that such a point means, we call it distance between, already this, everything is, then this point is, what is the relation between this x is in A, then we define normally what we define this, distance between x and y equal to infimum of distance between x is, I mean we cannot define infimum of distance between x, y is itself x and A. Infimum of distance between x and A such that A belongs to capital A, like that. Such a point x is, if it is a compact convex set, and that means if they understood, it is something called approximatively compact, which was introduced by I think Finolo or something. You can see that one approximation theory by Singer or some in non-linear space. I mean very artificial, look like artificial, but again it has very interesting application later. See, we want to find a nearest point. What is this? Distance between the point x and A, we have seen that infimum or greatest lower bound of distance between x and A belongs to A. This implies that this under here infimum is the x, I mean lower bound is there, this exists. Then we call alpha. Alpha is already among the lower bound, among the lower bound the greatest. If we give any natural number n, then alpha minus 1 is not a lower bound. That means what? Not a lower bound, because that itself already greatest. This cannot be a lower bound. That means what? There is at least one xn or A, call it xn from A, such that distance x and xn is lower bound. Lower bound is less than or equal to, now this will be greater than alpha minus 1 by n. Already this is a, then immediately prove that you can alpha, I have written correctly. Okay. Whether xn converges to x, we cannot, there exists a sequence xn in A which converges to alpha c. What about alpha less distance between x and xn? Because xn is in A, this is lower bound, but this is less than, if you want write that alpha. So that means what?
Limit is also yes.
Limiting case, it we can prove that okay, if we complete the xn, so properties of infimum and supremum is alpha is supremum of x in A, means there is a sequence which converges to the infimum or supremum. So that to complete, so that means what? We will get a sequence in A such that distance between xn and x converges to distance between the point xn set. Okay. Now, but what we are searching? We are searching a point in the set A. So what will be the some artificial condition, that's why xn is a sequence in A. Suppose if that sequence itself converges, then we can the x goes to distance between the point x and A is a continuous function. A point, a non-empty set in a metric space, x image is distance between the point x and set A. Distance means infimum, distance between x and small a in capital A. That is not a metric. Then it converges means you can take the limit both. Suppose xn converges to y. That means limit distance between y and x less than or equal to xa. So then that will imply distance between xy equal to distance between xa. So motivated by this, suppose this such sequences are called, there may be more than one sequence. Xn is, x is in capital X, xn is a sequence in A, so the distance between xn and x converges to distance between x and A. Then such a sequence is called minimizing sequence. Okay, forget about the name. If this is so, then xn has a subsequence which converges to an element in A. Then that is called, if such a thing happens, that set is called approximatively compact. In R, every closed set is approximately compact. In a finite dimensional vector space, every closed set is compact. In a Hilbert space, closed convex set is approximatively compact. See, but note that even unit ball in an infinite dimensional space cannot be compact. It is closed convex, but it is approximatively compact. That's why we may feel, what is that so artificial, but that is sufficient, that artificial, look artificial condition sufficient to get set of all best approximation, nearest point. Then for each x, yes. So we have a map X metric space, or X A is a approximatively compact convex set. That's why don't worry about approximately compact. Compact set, just a compact subset of a metric space. Then this we call it P suffix A of X. That is what? Those elements in A such that distance between, that is the nearest point. Distance between X and Y equal to distance between X and A, like that. This is non-empty, that means it is a set valued map. And this, that means X goes to Tx, in this case it is P suffix of X, A compact set exercise. This is a upper semi-continuous map. Anyhow, thank you very much. Extra, few minutes extra because we took some extra time, tea time. Okay. Thank you very much. And you have still any question, please feel free to ask. But the exercise, some of the exercise, please try your best and feel free to discuss if you are not able to solve or if you want to discuss.
Thank you, Professor Veermani. You have discussed multi-value maps in the context of fixed point theory, Nash equilibrium point. Really, in game theory, the Nash equilibrium is very important. We know actually theoretically, without knowing the equilibrium, when you apply in the game theory, we have a good number of occasions that we use this equilibrium. But it is in the very idealistic mode only, idealistic condition only. Then only the Nash equilibrium is applied. But in the, I think in the real world scenario is very difficult.
Yeah, that is.
Real world, because there is no equality. If equality is there, means like demand and supply, if you talk about the demand and supply is fine. If the demand is there, supply is there, and they coincide, then it's fine. If they don't coincide, then the issue comes. And okay, this is a really very interesting part of functional analysis, but you will wonder to know that in artificial intelligence and the machine learning, the game theory has paved a pivotal role. And now these days, AI students are offered one full course in game theory, AI and ML students. Yeah, in triple IT, most of the triple ITs, they are offering complete one paper in game theory, machine learning, and later on followed by the deep learning. So they are training the machine for the such games. So they use the Nash equilibrium and all sorts of games what we have done. Apart from that also, how you can see in your emails, the filters are there. Apart from the filters, the machine has trained in such a manner that all the incoming mails, they are sorted out into spam as well as your inboxes. So you have seen that this is the recent development only because of the AI. And they move to the spam, and there are the occasion also sometimes. Suppose I don't know Professor Veermani, and Veermani is sending me the mail. And actually the firewall is so strong that my machine could not understand that this is the mail from Veermani who knows me very well. So unless I say that yes, Veermani is known to me, it will not accept as an inbox mail, it will send it to the spam. So there is the chances that inbox mails also may go to spam, and there are some spam mails which are supposed to move to the inbox. There are the mails that they are in inbox, they have to go to the spam also. So here the concept of the game theory comes. Here we use the probability also in game theory. So rightly he said, of course he is using the multi-value mappings, etc. If you read the Hilbert space theory and applications, you will find at the end there is an application in the game theory also. In Hilbert space, that is H1 cross S2. Yeah, you are talking about the Cartesian product also here, the same thing. Really it is very interesting. So if you, those who have a little bit interest in the programming part also, they can use it for the programming. And finite dimensional, anyway your machine is not infinite. Your data is always finite. You can say countably, I am not countable, count all the data, but definitely is finite. Only in mathematics we can say infinite, but there is no infinity. is finite only in terms of the data. So definitely you have solution or no solution. That is possible. So he dealt very nicely this game theory, and actually I have seen around 20-25 years back one book is there, Bauer's fixed point theorems, application in game theory. Yeah, long back in Ramanujan Institute I have taken there.
Most of the earlier stage only they used Bauer fixed point theorem.
Bauer fixed point theorem. I do remember morning also Professor Brinde, he was talking about the summability. Olden days the people, they were working earlier in summability only. Few of them shifted into the Fourier analysis or the Fourier series, and some of them shifted to the functional analysis. Like he was talking about the Billy Rhodes. Billy Rhodes worked a lot in summability. I studied summability when I was in MSc. MSc final year we have a paper in finite series. So, sorry, divergent series. The name is divergent series and the book is also same. That is our G.H. Hardy. G.H. Hardy's book. I studied that book, G.H. Hardy, and part of that book is infinite series. Sorry, divergent series. So, though they are shifted, some of them shifted into functional series. Later on, those who have not shifted into functional series, they shifted to Fourier, and after the Fourier, there are many people, they have shifted to spline, like Professor S.P. Singh from Canada, Montreal. He shifted to spline also. Spline, yes, spline, and then approximation. Spline approximation. After the spline approximation, there are many people, they started working on the this CGD, computer aided geometric design modeling, and they started using the Bezier-Bernstein polynomials. Bezier polynomials, you heard about those who are working with the approximation theory, they know that what is the Bezier polynomials. And Bezier and Bernstein, these polynomials they use. In this there are some people like C.A. Micheli, who is from US. I think you met him. He was in US, and Daman. Daman, he was from Germany. They both shifted in this CAGD, the computer geometry design modeling, and after a long time, the first time the Mercedes Benz was designed using 100% this mathematics, they used the convex functions. Convex functions, and they use the Bezier polynomials, and using the CAGD, that whole design was changed. Earlier Benz, and now these days what the Benz you are finding is because of the mathematics. So such a strong mathematical background is there, but only we have to look into that how to apply such mathematics. It's a tremendous subject, and in this scenario we people of course started our work, like professor also and others also. We started in the pure mathematics, but pure mathematics has the immense applications. You people are 20-25 plus or around 25, so you have the more bright chances to apply our mathematics by using the computers. Definitely you need to know the programming languages also, and now these days the programming language means best is you forget other programming language, you come with and update yourself with the Python programming. Python is really unbeaten, and you have the community support in Python also. Like what in the game theory also, you can use the Python, because lot of intuitions are there in that programming. You find good number of libraries also in that programming language, Python, which is of course a high programming language, but highly mathematical support in the Python programming. So you try to pay some interest into the Python, and among you, maybe I don't know about those who are the faculties, they may know, but I can assure you there are some student participants, they know Python. You can interact with them, or let those people interact with them, then they can explain you how the Python is impacting a lot. So lot of games can be created using this, and you have more chances of getting very good and innovative results. Okay. So any question from the participant to ask Veermani sir? Maybe tomorrow, I don't know, but if tomorrow possible, we will see. Day after tomorrow, we will have the open session interactions, because our day after tomorrow, we have only one day left. See, first day we feel, oh, 5 days are there, and after today you will find that, oh, only 3 days left. See, this happens. When the days come, this is the countdown. This is something like that, end of our days has come. So life also like that. So end comes. Yeah.
And you can see that the book itself is with us.
Yeah. So after tomorrow, you feel that, oh, only 2 days left. If this could be prolonged further 1 or 2 days, it was good actually. But on the first day, definitely you felt, oh, we have to sit so long time. But when you go back to your home, then only you can realize that this hectic schedule is going to pay you something. And I do assure that. So if no question, I think we can close the session today.
I think I wanted to say only one thing. You know, we cannot talk with the books, but book is itself, so you can utilize. What I am telling is Professor Veermani sir is with you, so you can, whenever you get a chance, you interact.
And there is no bar that he is somewhere in the guest house and you cannot. You can squeeze, man, anybody. Squeeze. Whether they are in guest house, while they are walking, anywhere. I find that there are some people, even they are in the washroom, and if they are commonly going in the washroom, they are talking in the washroom also. I have seen, that's why I am telling you. I have good experience, and I think the brain is working more when you are in washroom. I don't know why, but that's true. That's true. Okay, so shall we close today? Okay, thank you very much, participants. I think very nice day today. Hectic, of course, but we have learned lot of things, variety of mappings. Okay, whether is a fixed point, a proximity point, approximation. Okay, so now you have the visualization that how fixed is very rigid. Fixed point is very rigid, and what point he is talking about is not rigid. If you are very hungry, so possibly that your hungerness may be controlled by some sort of food, but this is also possible that if you are hammered mentally, tortured mentally, your hungerness may go. So he is torturing you mentally that you should not eat anything, but your hungerness should go. Okay? Right. Thank you very much. Thank you, our faculty members also. Thanks a lot.